Morning to everybody. So today we are going to talk about the geomorphic methods for identification and characterization of active faults, geomorphic markers of tectonic deformation. So these are the books which you can follow, like Tectonic Geomorphology by Douglas W. Burbank and Plate Tectonics, How It Works. So these are the books, and there are other more books. But Tectonic Geomorphology is a good book if you want to go into more detail. So we will be discussing the geomorphic markers, faults, what is the difference between a fault and an active fault, and then establishing timing in the landscape, dating methods, right? These are the things which we are going to cover. So first of all, we can see that Indian plate has moved from south towards north, and it has traveled a distance of roughly 6,000 kilometers. And we can see that the movement basically is like 180 millimeter per year, and this rate has changed. So currently it's around 4 to 5 centimeters per year. And just to because we are in Chandigarh and we are very close to Himalayas, so one very important boundary basically, and we have this 2,500-kilometer Himalayan arc. And we are this Indian plate is basically colliding with the Eurasian plate, and there is a northward movement of 4 to 5 centimeter per year. So this is a bigger concern because we have a lot of population in this area, and we have a lot of active faults and earthquakes. So there is a need to understand that how these things will work out in future, because we have a lot of dams also in Himachal. So just a very, there are many definitions of active faults. There are papers discussing different things, but we are just going to use the simple definition. If there is an activity, if there is an earthquake, let's say, if we put in a simple terms within the Holocene, then maybe we can call it as an active fault. Okay, so that is roughly like, if in within, let's say, last 10,000 years, there is a earthquake, along a fault, then we can call it as an active fault. Then, in Pleistocene times, we can call it as a potentially active, and then in pre-Pleistocene, we can call it as an inactive. So this thing we have to keep in mind. So a lot of figure basically shows a lot of earthquakes, in the Himalaya. These are epicenters. So, very close to Chandigarh, Kangra, and there were these major earthquakes very close to us. There was in 1905 the Kangra earthquake, and the magnitude was like roughly 7.8. And there are other bigger earthquakes along this region. So that is again a motivation to understand earthquakes and active faults. So this is just a diagram showing that the major thrust in the Himalayan belt are basically dipping towards north. And most of our work, which we have done uh, in this area, basically is concentrated along Himalayan frontal thrust, which is very close to this. You can see the Shivaliks, so very close to Shivaliks. We have worked basically in this part, in the frontal part, mostly. So if we are compressing, let's say, if we are now compressing this Himalayan, so any fault can be activated anytime, you know. So that is, and then, maybe there is one fault is activated, maybe two are activated, or, it can be a combination of these things. So Chandigarh lies in seismic zone 4. So this is just a simple diagram showing the different type of faults. So we can have normal fault, strike slip fault, or a reverse fault. So very, uh, very. So can we say that whether this is an active fault or not? How can we say that? Yes. So if there is a movement, but how do we know when this movement happened? you know, how can we quantify that, that this is an active fault, because we are using a kind of a definition of the earthquake happened in the last, let's say. Yes. Yeah. But yeah, but how do you know that's an active fault? That's the question. Dating. So what do you want to date basically? So simply you can think of that. Let's say there is a river which is coming and it is bringing some sediments, and these sediments are deposited along any fault, right? So these sediments are deposited in layers. If the sediment age is from, let's say, 0 to 10,000 or 12,000, you know, and if those sediments are displaced, that means these are, Holocene or quaternary sediments, Holocene. So if those sediments are displaced, then we are able to say, yes, this is an active fault. So we need these quaternary sediments which are deposited on top of a fault boundary, and if these sediments are displaced, and then we date those sediments, and then we can quantify, yes, this displacement happened in the Holocene. Then we can call it as an active fault. Otherwise, we can simply say that's in fault. Okay. So now we are going to discuss basically the tectonic geomorphology. Uh, so because plates are moving, we are having this elevation. And because of this elevation, there is always a competition between the topography and the erosion. And in order to understand what's going on, basically we can have some geomorphic markers. So geomorphic markers, what are geomorphic markers? These are landscape features such as marine or fluvial terraces that can be used to track deformation. Prior to deformation, the surface of these markers represent planar or linear features with a known geometry that can be predictably tracked across the landscape. So yes, we will discuss a little bit more about these geomorphic markers in the coming slides. So techniques and some of the insights gained from them. In many ways, this greatly improved understanding of modern deformation that we now can take the largest strides in interpreting the past deformation and landscape evolution. So uh, basically, we are in Chandigarh right now, right? And we know that we don't have floods in Chandigarh. You know. So you can think about it, that why don't we have floods in Chandigarh? But very close to Chandigarh, for example, in Ropar, where we have IIT Ropar, there we have floods, you know. So the question comes to our mind, what is the geomorphology, or how the geomorphology of Chandigarh has evolved, or how this landscape has evolved through time, that why we don't have floods in Chandigarh? So that is a very, interesting question you can ask yourself as a, student of geology. So we will also discuss, how this landscape has evolved through time. So now if we see the this diagram, uh, basically on the x-axis we have time, and then we are going from fully interglacial to fully glacial periods. So during Holocene, you can see that we are mostly in the interglacial period, right? So it is important to understand that if and the second scale, we are seeing one full cycle, one full climate cycle, because and then in the third diagram, basically we are looking at there at a scale of 1 million. We have many fully interglacial and fully glacial periods. So why this diagram is important? Because when we are dealing with sediments, we need to understand what is the age of those sediments. If let's say that we have some river terrace, and I will discuss also river terrace, how they're formed. But right now we can just think that a river brought some sediments and those were deposited. If the age of those sediment is, let's say, it varies from 0 to 5,000, can we study climate, or can we study, that climatic variation in those sediments? If the yes or no? No. Why we cannot study the climatic variation? Because the sediment has only seen the climate of only fully interglacial. It has not seen the complete cycle. So that means those sediments are only deposited during the erosional processes which happen during the fully interglacial period, right? So because we have these, river terraces of different ages. So yes, you can have a deposition because of, a lot of rainfall is happening, or it may be just land is uplifted. So always these two components, whether it is a tectonic or whether it's just a climate. Climate is like a rainfall. You have more rainfall, you have more erosion, and then you have position. So this thing is very important to keep in mind when we are looking at sediments. So if let's say there is a, deposition, some sediments are there, you find in Himalayas, let's say, and the age varies from, let's say, uh, 0 to, let's say, 1 million. That means now these sediments are deposited during various glacial and interglacial periods. So now those sediments can have different climatic zones. If you date them, you can do those kind of interpretation because those sediments are older now. So I think that is clear. Yeah. Okay. So now in Holocene, we can see that we are always in the fully interglacial period. That means we have an advantage. We have an advantage in Holocene. What is that advantage? That if we are in Holocene sediments, we are not seeing the climate cycle. So if we have any kind of deformation, that means that is maybe if the sediments are displaced, that is because of a deformation. So at Holocene timescales, we are confined to a post-glacial era in which the climatic conditions have varied relatively little. You know. So we are not, at a time scale of 100,000 or more, complete or multiple glacial interglacial cycles have occurred. At Holocene timescales, cause and effect can be examined rather directly. For example, if faulting causes the land surface to tilt in a given direction, the timing and the rate of diversion of the river in response to that tilt can be measured. So now, what are the strong imprints on the landslide? What are these drivers basically? What are these major drivers which are driving this tectonic geomorphology or, So these are basically the large scale changes are sea level. If the sea level changes, then the size of the glaciers and the discharge of the river. So these are the main drivers, that generate the different type of geomorphic markers. So these are the main drivers. For example, if you see the Himalayan terrain, you can see the sediments are present along the rivers. So those sediments can be, brought by the river. But sometimes we see the villages are on the top of the mountain where the river cannot flow. So those sediments maybe are of glacial origin. So if you think in terms of like, okay, from where these sediments are coming, either they are glacial, they're glacially generated, or broadly we can say they are fluvial, right? So if there is a village on the top of a mountain, close of the mountain, maybe the glacier was present there, and it did erosion and everything. Now the maybe the glacier has melted, but the soil is there preserved on the top of the mountain where the village is situated, right? So these are, very roughly we can divide, okay, the glaciers might have generated those soils and the discharge of. So now the question is like at a time scale of a millions year of more, then numerous climate cycles have created that time average landscape, right? So sometimes we can have three disadvantages which we have in Holocene. The rate of tectonic processes may vary significantly slow or occurrence of deformational events such as earthquake may be sufficiently rare that tectonic signal is obscure. Second, the rate of geomorphic processes that Holocene interglacial times may not be very representative of a long-term rate. So these are the Because we are in Holocene, so we might calculate some rate, but that may not be a representative rate of the bigger time scale. The time it takes for a geomorphic system to respond to a change imposed by tectonic forcing can longer can be longer than the Holocene. You know, maybe there is some kind of a tectonic event or something, but the response we see in sediments, maybe it will take more time than the Holocene to occur. So these are some disadvantages. Because the geomorphic system may be in a state of transition with respect to tectonic perturbations imposed upon it. So the present rate of crustal deformation can be compared against the sediment load of the rivers. So these are common example is like the river terraces are almost untouched by erosion and can function as pristine recorders of Holocene deformation. The strength of Holocene studies is that the record is often most complete, the dating is most precise, the rates of many competing processes can be directly measured, and the interaction can be examined. So there are some models which landscape development models which are proposed by different scientists. So first one is the Davis model. Basically, Davis proposed in during 1800s and 1900s that he gave the concept of youth, maturity, and old age. So the tectonic forcing is a impulsive phenomenon that occurs at the beginning of the geomorphic cycle. All of the building of the topography occurs at the start of the cycle. So in this case, we can see that this tectonic forcing or the uplift is basically happening in the beginning, and then slowly and slowly there is a decline, and so the landscape basically evolves from youth, maturity, and old age. Today in the afternoon, we are also going to do the practical, which in this, something like that we can discuss. Okay. So the first thing is that in Davis model, the rock is uplifted instantaneously. And then you have this, slowly and slowly this tectonic forcing is eroded by these different processes, erosional processes. And another scientist, he gave another different idea. He said that, okay, the tectonic forcing is not just instantaneously. Slowly and slowly, you are building the topography. As it is being built up, it is also being, cut down by the erosional forces. So there is waxing and waning, and in this model, it's like a wave, like a pattern of tectonic forcing through time. So that's the second model. Geomorphic processes were conceived as attacking the uplifting region through the period of mountain building, so that the result of landscape could be interpreted as a product of this competition between deformation and erosion. As the rate of mountain building waned, erosion was proposed to overtake deformational rates, thereby causing a gradual reduction in the residual topography. There is another model, basically landscape development model proposed by Hag, who suggested that the rate of deformation and the rate of erosion are sustained for long time intervals. The landscape will come to a sort of balance or dynamic equilibrium. So he proposed a different, so given the finite strength of the rock, Hag realized that topography cannot increase without limit, even if the rates of tectonic forcing persisted for very long periods. In this is different than you know Davis model. That in Davis model you have instantaneous tectonic forcing, but in this case the relief is built slowly and slowly, and then basically there is a equilibrium, dynamic equilibrium between topography and erosion. So as the topography grew and grew, the relief on the hill slope would create forces exceeding the rock strength, and they would collapse. Right? If we just keep on increasing the elevation of the rocks. So at some time, because of gravitational forces, the rocks will collapse. So those will that will cause basically landslides. With continued uplift of the bedrock, additional slow failures could limit the height and the topography would attain. Eventually, the topography would enter into a roughly steady state or a dynamic equilibrium. Consequently, in this model, rate of mountain building and rate of erosion would come into a long-term balance. So if we think that the if the dynamic equilibrium means that the rate of uplift and the rate of erosion is more or less same. So in that case, we can say it's a dynamic equilibrium. Unlike the models of Davis and Planck, there is no need for rate of deformation to become negligible or even to wane at all. That is basically in the Hack model. So uh, in our area, in this Himalayan zone, we can now see that, let's say this is a drainage basin. And if there are different tributaries which are joining the main trunk. And if there is a, let's say there is a fault, you know, let's say there is a fault in front of this, like a, let's say normal fault or something. So if there is a fault right here, this main trunk, it will know, yes, there is a drop of elevation, right? But this one and other tributaries which are behind in this drainage basin, those will not see the change that there is a drop of elevation. So the erosion will start happening first here, and then it will propagate. First, it will come to this point, and then this small stream will understand, okay, there is some drop. Now the erosion will start happening here. And like that, it will progress through the drainage basin. So the channel that crosses the fault sees the displacement first, right? The local base level will have fallen abruptly, causing the river gradient to steepen locally and erosion of the channel to intensify. At this point, all other positions in the catchment will have been undisturbed by the faulting event. So the faulting elicits no initial geomorphic response. So the point is why we are discussing this, that there is a time lag. There is a time lag between tectonic forcing and sediment response. This is an important concept. We need to understand that there is a time lag. So the time lag between the tectonic forcing and sediment response is variable. So Cui and Binot in 1996 developed a model that predicts a lag between the onset of deformation and the response of a geomorphic system to the deformation. So in this, we can see this is a, we have a tectonic influx right here, you know, and it took some time to erode this, tectonic or impulsive system. And the sediment influx had the maximum peak somewhere here. So there is a time lag, between the tectonic, this thing and the response. The overall response of the geomorphic system and the magnitude of the lag depends strongly on the nature of tectonic forcing. If the forcing is impulsive, like as we discussed in the Davis model, then the topography is rapidly created, degrades through time. In tank model, if the deformation increases to a maximum through the time and then wanes, topography gradually builds in the phase of progressively increasing rate of erosion. The maximum topographic expression occurs slightly after the rate of deformation begins to wane because the rock uplift still outpaces the rate of erosion. So again, we can see that there is, a lag between these. In the hack model, if we can see that as the change in the rate of surrounding forcing would push the system towards a new equilibrium, whereas cessation of deformation would return the system to almost Lewisian state in which the topography is systematically degraded. So finally, in the later half of the cycle, the topography wanes despite gradually diminishing rates of erosion. If the tectonic forcing is continuously sustained, then Huyen Binot model predicts that after an initial interval of building of topography, the rates of rock uplift and erosion will become balanced, and the topography will be in a persistent dynamic equilibrium. This is just an image just to show that we can use uh, lidar, and in this case we are able to see a fault in active fault and also glaciated sculptural topography. So the question is, yes. So question: can enhanced erosion drive up uplift of a mountain summit? So let's say if there is a mountain and we are doing erosion, right? There is a lot of rainfall in Himalayas and the rivers are bringing sediments. So can this cause the mountain to rise above? Yes. Okay. Yes. So yes. So we will discuss that, and yes, the answer is yes. And so we can think of a ice cube basically floating in water. So 10% of the iceberg is basically above the water level and 90% below, right? And if we start taking that ice from above, because of buoyancy forces, the iceberg will rise up. Same thing happens in the mountains. So, for example, this is the ice cube, and this is the original height of the summits. And let's say we have eroded in between, mass. So now, because of this isostatic compensation, you know, the the relief is increased, and we can see that the change in the summit height. So we can see the change is there, and the change in the mean height also, because change mean height was below there. Now it is up. Point. Okay, I can just. हाँ, तो ठीक है. ओके, मैं ठीक है. ठीक है. Okay. So in paleoseismological studies, what we do is study of basically past earthquakes, and we want to understand what is the reoccurrence interval. So paleoseismology, yes. So for example, like this, So let's say in this case, what we are looking at is basically the trace of the fault, and on the y-axis we have amount of displacement. So we can think of it as like let's say there is a fault and there is an earthquake along this fault. So it ruptured in the similar manner. So earthquake 1, earthquake 2, and earthquake 3, they're rupturing in a similar manner and a repeated magnitude of offset at any location. So these we can call it as a characteristic earthquake. But a random earthquake, on the other hand, if we have a fault trace, then earthquake 1 and earthquake 2, the rupture length is different and the location is also varying. So we can call these as random earthquakes. So non-steady state changing relief and non-steady state changing mean elevation in this and steady state topography. So such constraints present some great challenges to researchers in tectonic geomorphology. Morphology. It is inadequate to document any modern rates. The rates for interval throughout a climate cycle or the rates that integrate an entire cycle are needed. This integration requires clever ways to measure quantities of material removed from and added to a landscape. So four attributes of Himalayan Tibetan origin and how they may be linked. So first, the thickening of the crust beneath the Tibetan plateau appears to have caused crustal melting of at least some of the lower crust, which then becomes weak and tend to flow towards as a channel confined above or below by a stronger rock. Secondly, the rocks of the Greater Himalaya are bounded by two large faults that have been active at the same time. below the Greater Himalayan rocks, the MCT, is an up to south thrust, whereas above them, the Tibetan detachment is a down to north normal fault. Third, every summer, the monsoon in the Indian monsoon dumps about 4 meters of rainfall on the southern flank of the Greater Himalaya, but less than 10% of that amount penetrates into across this decreasing rainfall gradient. Current erosion rates are diminished by 3 to 4 fold. So, for combining these observations, some geologists suggest that the intense monsoon driven erosion on the southern flank of Himalayan weakened the underlying crust and drew the partial melt channel toward the surface, thereby determining where the big faults bounding the channel are located. So this is one model basically in which we have lot of this erosion basically above MCT, and then this partial melt of this channel basically flows towards that. So this is basically a proposed climate tectonic coupling in the Himalayan orogeny. Okay. So now we will discuss some of the geomorphic markers. So these are the geomorphic markers, basically glacier. And so, what is a geomorphic marker? A linear identifiable geomorphic marker, planar or linear, that quantifies the amount of deformation change that has occurred due to geomorphic processes over the geological past. And the important parameters for a geomorphic marker, that we should know the initial undeformed geometry, and we should know the high reservation potential. Important. These are the three important parameters of a geomorphic marker. So in this case, we have this alluvial fan, like this alluvial fan or a penny plane. So these surfaces can represent as a geomorphic marker. So when we think, it has to be either planar or a linear, right? A geomorphic marker has to be planar, like a plane, or it can be a linear. And so that we know it's undeformed geometry, because after deformation, we know that that deformation happened in this. So linear geomorphic marker include naturally occurring linear features such as lavies, glacial moraines, man-made linear features like fences, lines, railroad tracks, sidewalks, etc. Planar geomorphic markers include river terraces, alluvial fans, delta marine terraces. So both these geomorphic markers are used to determine deformation or changes. So marine terraces, beaches, and shorelines, they can also they can have constructional and destructional uh, act as constructional and destructional geomorphic markers. Uh, One important thing is that the global or isostatic sea level changes within the Pleistocene are caused primarily by change in the volume of continental ice sheets. Associated swing in the sea level are huge, 120 to 150 meters. So sea level, we know the height of Chandigarh is approximately 330 meters. If the sea level rises 150 meter above, in the Bombay, so half of the India will be drowned. So you can think that 150 meter of sea level rise. You know, so these are the rises which happened in the past. The order of magnitude approximately 120 to 150 meters. So these surfaces, uh, these marine erosional terraces, they can also act as a geomorphic marker. I think we will discuss more, river terraces actually, because we are close to the Himalayas. So I think I will quickly jump to the uh, Yeah. So this slide is also important. We can see that, there are sea level changes. A lot of these sea level changes are there, and people work on these things also. Okay. So river terrace is again, okay. The one question is whether river terrace is a planar or a linear geomorphic marker. Anybody for linear? Okay. So yes, river terrace is a planar geomorph because it's a plane. It's like a plane, right? It's a 2D plane. You can think of it as a 2D plane. So river terrace is a planar geomorphic marker. So river terraces are step-like landform that extend along the sides of a valley. And very close to, all of us know that Sukna Lake is there in Chandigarh. So if we go towards east, there is a river. The name of the river is Ghaggar River. In Ghaggar River, we have five different river terraces, right? So my question to you is, tell me whether those river terraces are formed because of erosion in the Himalaya or there is something else also, you know. So if we just go towards river Ghaggar, we can see there are five river terraces, right? Okay. So yes, we will discuss that. They form by vertical erosion of a former floodplain by river resulting in a new floodplain that abandoning the older floodplain at a higher altitude. Factors that influence the behavior of rivers, stream power, sediment load, competence of the sediment, roughness of the bed. Threshold of critical power, a river that neither aggrades or degrades is considered to be in equilibrium, and thus it is at a threshold of critical power. At this stage, stream power is just sufficient to transport the sediment load and the height of the bed remains constant. So in this figure, we can see that there are different river terraces. So T1, T2, T3, and there is, the front channel. So Schmidt will tell me what is the oldest river terrace. T1, but in geology we have always, the lower rock is the older, but here it is totally different. So this is the oldest river terrace. This is younger. This is so it's reverse. In case of a river terrace, we have the oldest river terrace on the top, and younger is down. Why is the critical power important? It indicates the potential linkage among the different variables. So just how changes in climate or tectonics would cause the river to switch from aggradation to degradation or vice versa. Okay. So now there are different types of river terraces. There are aggradational terraces, you know. So result from aggradation of the river transported alluvium along a river course, followed by down cutting, which leaves the former aggradational surface abundant as a terrace. This is a consequence of crossing of the threshold of critical power such that river moves from aggradational mode to degradational mode. So we can think of that, in the first flood, the river terrace F1 is filled, so the river deposited material up to this point. And in the second case, when the river came, it eroded its part and then it posted this. And third time this. So this is older and this is younger, this is the youngest. So this is an example of a gradation where basically river is depositing material and then again cutting it down. Degradational terraces. Now in degradational terraces, there are two types: paired river terraces and unpaired river terraces. So paired river terraces, they form where downcutting by water is greater than lateral migration of river channel, result in same elevation on either sides. Correlative terraces are preserved in both sides of the river. So in this case, we can see that T1 is present on the both side, T2 is also present. So this is an example of a paired river terrace. Uh, Unpaired river terraces, now in case of Ghaggar River, where we have five river terraces. So all these river terraces are present only on the right side of the river. But on the other bank, left bank, you don't have any river terrace. So this is the Ghaggar then represents an example of a unpaired river terraces. So they form where the lateral migration of river channel is greater than vertical down-cutting water movement. So you know the city Panchkula. Panchkula is adjacent to Chandigarh. So the Ghaggar River used to flow in Panchkula through Mansa Devi area. So it actually migrated 2-3 kilometers towards east. So because of this lateral migration, we have no river terraces, so unpaired river terraces basically in Ghaggar River. So Ghaggar River represents an example of a degradation of unpaired river terraces. Now, question is, what is the use of these river terraces in tectonic geomorphology? So three groups of processes promote river terraces. So now the question is how these river terraces are formed. A crustal movement, uplift, can be one reason for the formation of a river terrace. Second is sea level changes. I think what is happening in the frontal part of the Himalaya. I will say that sea level will not affect the formation of river terraces in the frontal part of Himalaya. I mean, uh, then climate change. So when we say climate, that means maybe we will have a lot of rainfall in the Himalaya and lot of sediments will come. Maybe that can fill like a river somewhere. So maybe next time the river is cutting those sediments. So it can be so river terrace can be purely due to climate or maybe because of tectonics or both the combination of tectonics and climate. So how can we use river terraces to calculate tectonic rates? The age of the river terrace must be known. So we need a method by which we can understand how, that what is the height of the uh, river terrace from the current river channel and what is the age of those sediments. So in order to calculate age, basically we use OSL dating, optical luminance dating, in order to understand what is the age of the river terrace. So alluvial fans, yes, alluvial fans can be used again because now alluvial fan represents a linear geomorphic marker or it's a planar geomorphic marker. Planar? Yes. So it's again a planar surface. So right. Alluvial fan again represents a planar geomorphic marker. So in Uttarakhand, we have a place where you have MBT, main boundary thrust, and it is displacing this. So we know that these sediments are deposited in, one go, but that is displacing this geomorphic marker. So if there is some kind of a displacement along a alluvial fan, then again it can be dated and it can be, shown that this is a uh, uh, tonic or active tectonics is going on in that area. We have a Logard fault, this fault where ambit is active actually. So sometimes two alluvial fans might merge, so the elevation profile might change where they are merging. And also in Pinjordon, uh, behind Shivaliks, in the Shivalik Chandigarh anticline, behind Chandigarh anticline, we have Pinjordon, and there are again these alluvial fans which are tilted because of tectonic deformation there, and there are a lot of active faults which are causing the deformation of these uh, alluvial surfaces. Lava flow, debris flow, and landslide. Despite the meter scale roughness of the upper surface of most lava flows, the surface of elongated flow can provide excellent geomorphic markers. Maybe not used here, but where you can have some volcanic activity going there, those is topographic gradients along the flow surface can be measured directly, and numerous surface features can be recognized for cross-cut correlation, cross fault correlation. Landslides, yes, landslide. If basically, what happens is that there is mass movement and all the material is deposited at once. So landslide has a advantage that you can date this. For example, this is again a debris flow. So if you just date it, you will get one precise date given the errors because this event happened instantaneously, more or less. So that advantage we have, and so the age of the deposit is closely related to we can pinpoint the age when this event happened if it can be dated. Erosional surfaces during long intervals of tectonic quiescence. Topography can be believed of by erosional processes and a low relief landscape can be produced. Isolated erosional remnants may be surrounded by piedmonts, erosional surfaces of low relief carved into bedrock. Across broader geographic regions, peneplains characterized by slightly undulating and generally featureless topography can result from long continued erosion and deposition in absence of tectonic deformation. So we can see that this area is totally peneplain. So if you go to Odisha, in India, you will see this kind of topography. All these areas are sometimes you have iron mines and other things, but more or less the topography is like this because there is no tectonic activity and it was a part of Gondwana and it separated from Antarctica. But if you go to Odisha, you will see this kind of topography there because from long time these hills are eroded and eroded. Now they have this you know shape. So when such erosional processes formed in distant geological past, they were commonly buried by subsequent deposition, such as regionally extensive unconformities preserved. So when such low relief surfaces, piedmonts, peneplains, regional unconformities are uplifted tectonically, they can form prominent markers in the landscape. So yes, sometimes these planiplanes can also be used as a marker. For example, like a lot of these, we see that these river terraces are not dated at many places. So people sometimes use elevation. They use elevation just to because they are dating one river terrace, for example, here. But at other places, they are just taking elevation and they are thinking that the age of this surface is same. They may not have just dated it, but it's just a relative dating or relative method of calculating age. So rivers and ridges crest. The course of the river and the ridge crest that are displaced across a strike slip fault can clearly record the literal offsets. In this case, we have a stream which is coming, and then there is a strike slip fault which is causing the beheaded streams. And in this case, then we can calculate what is the offset of the stream, and from that we can calculate the whether it's a strike slip fault, dextral fault, sinistral fault. So that kind of information we can calculate. So here, very close to this, we in Sathon basically we have a strike slip fault, and it is showing the same feature which as it is shown here. It is showing a right lateral movement there. So these strike slip faults, if you cut this stream, so that stream is basically displaced, and that displacement can be measured, right, to understand what is going on. And then glacial moraines. So they are linear geomorphic markers. They are remnant soil and rock left behind by moving glaciers. They have an obvious direct relation with climate change. When we consider glacial moraines a good geomorphic marker, when moraines are associated with most recent advances, although an absolute age is always preferred, an approximate age can be assigned to the undated moraines and tectonic rates. With appropriate uncertainties, can be calculated based on the observed offsets. Mostly common encountered problems with markers. What kind of problems we can face? Most typical difficulty in extracting the maximum information from a display geomorphic marker in the absence of well-documented age for the surface. We need to have age. Knowledge of array of available dating tools, experience with the appropriate field procedures for collecting suitable material for a specific dating, and through an innovative approach of the problem of defining geomorphic ages is needed to obtain reliable age constraints and hence the deformation rates. Correlation of partial preserved geomorphic features present other challenges. As older and older markers are examined, their preservation typically becomes increasingly elementary. So preservation of, sometimes we don't have geomorphic markers everywhere. So that is again a challenge. Okay. Okay. So basically, we learned that we can have planar geomorphic markers, we can have linear geomorphic markers, and if there is any deformation in that, then we can date that and we can try to understand. So establishing the timing in the landscape, so we need some kind of dating. The science of tectonic geomorphology strongly relies on placing time controls on the landscape. Uh, until the advent of radioactive dating methods, the principal means of establishing timing in the landscape was through the use of relative dating methods. So, in this presentation, we will discuss a little bit about what is the difference between relative dating and absolute dating methods. The relative methods yield relational information only. Surface X is older than surface Y, which is in turn older than surface Z, as we do in geology. So this is a basically kind of a relative method of dating. Whereas absolute dating allows us to place a number on the age. For example, there is a terrace, river terrace, which is deposited. So X was created, let's say, 3,000 years before present. So in absolute dating, we don't need any kind of a relation with other features, you know. So that is the major difference between uh, relative dating and absolute dating methods. So absolute dating, the technique used to determine the exact age of the artifacts or a site using methods such as carbon dating. In relative dating, a technique used to determine which object or item is older in comparison to the other one. In absolute dating, we have a numerical age, and in relative dating, arrange fossils in an order. For example, paleontologists basically use fossils in order to know the age of the rock. So that is a relative method of dating. Four methods are radiometric dating, amino acid dating, dendrochronology, and thermoluminescence. And relative dating involves biostratigraphy, stratigraphy, and cross dating. And precision is high in case of absolute dating, and precision is low in case of relative dating. Quantitative measurement versus qualitative measurement. Uh, Absolute dating works better for igneous and metamorphic rocks, and relative dating works better for sedimentary rocks having layered arrangement of sediments. Expensive, so absolute dating is expensive and it takes time, and relative dating is less expensive and efficient. So this is just showing some of the absolute dating methods. Radiocarbon and C14 is used. So maximum age is around 35,000 years, which we can date, and the material used is wood or shells. And then thermoluminescence, the maximum 3,000 years, 300,000 years, and the material used is quartz or silt. Cosmogenic quartz and olivine is used 3 to 4 million years. and then paleomagnetic and biological, which is basically dendrochronology. Wood is used, it can go up to 10,000 years depending upon the existing of a local master chronology. So these are different methods. Basically, uh, in active fault or in when we study these active faults, we basically use the optical simulated luminance, that is OSL, and the material which is used is the quartz or the silt, which is present in the sand or the soil present there. So I think I will skip this part, dendrochronology. Radiocarbon dating, yes, it can be used. So naturally occurring isotope like C14 uh, to determine the age of the carbonaceous material up to 50,000 years. Maximum you can go up to 50,000 years, not beyond that. So raw uncalibrated radiocarbon ages are usually reported in uh, years before present. So this is just the natural radioactive decay of the radioactive material, and the radiocarbon clock is based on the known decay rate of unstable isotope of carbon C14, which is found when cosmic rays interact with the nitrogen in the atmosphere. The radiocarbon combines with oxygen to form a radioactive form of carbon dioxide. When a living organism dies, the carbon exchanges stops. Measuring the C14 concentration in the organic samples and provided they have not been contaminated by younger material, one can calculate the time elapsed since the material was originally formed. And illuminating basically, you know, uh, basically we have quartz, silt, and uranium, thorium, and potassium. It is present everywhere. We have this background radiation. So you can think of that. When this uh, quartz grain is exposed to sunlight or any light, you know, then the age of that sample will become zero. But once this quartz silt is sediment, it is buried under the ground, right? It is buried somewhere. And then you have in the background, you have uranium, thorium, and potassium, and those are bombarding. So this quartz will store some of the charge. Some of the electrons will go to the higher place. So it has stored some energy. So when we go in the field, basically we can take out this sample using a pipe, and then we can bring that sample into a dark room and open that, and then do chemical processing. And then we can put it into a machine to calculate how much energy is stored in that quartz. And the other thing we need to do is we need to also understand what is the background radiation there, what is the amount of uranium, thorium, and potassium which are present in that in the surrounding of that sample. So using those techniques, we can calculate the age of that sample. That is by basically using OSL. So in this diagram, basically this is what we are showing, that there is a uh, energy stored in the sample. So there is a erosion, transport, and then deposition. Again, then it was built up, and then if it is exposed to sunlight, then it is again you have a reset basically, and then it will just tell us the last depositional event. So if a sediment is exposed to sunlight, then its age will become zero. Okay, so it's like that. So this is what it is showing. You can have thermal or optically simulated luminance. And then there is another technique nowadays. It is used the cosmogenic surface exposure dating. It is again used to understand that if a surface is exposed, from how much time it is exposed to the atmosphere. So this is again a new technique which is used. So a constant rate of production, the number of atoms of beryllium and aluminum that accumulate in a rock surface will be proportional to the length of time the rock were exposed to cosmic ray bombardment. The amount of each nuclide would be estimated of the minimum time that the particular surface has been exposed. So if let's say there is a fault scarp or any surface which is exposed, and we want to know from how long this surface is exposed. And then in that case, this technique can be applied. It can tell you that how long this surface is exposed to the nuclear bombardment. So that is cosmogenic surface exposure ages we can get. And basically, this decreases with the depth, and depth is in centimeters or inches. Okay. So I think most of the things are covered by sir. So I will just discuss the things uh, which I think are. I mean, we can discuss some of the things, and then I would like to show some of the examples of the work which we have done. Uh, can we take a break? I think here a small break. Yeah. Okay. Okay. Small break. Okay. हाँ, किस तरह? हैं? क्या कह रही मैडम? मैंने ईयरफोन बंद किया हुआ, मैं तो प्रेजेंटेशन दे रहा हूँ। आया मुझे मैसेज, क्या कह रहे हैं? यार एक माउस, तुम्हारे पास माउस है क्या? एक माउस मिल जाएगा? हेलो, hello. Okay, so in this case, we are discussing the model for fault displacement patterns. So in the first case, we can have a propagation fold. You know, basically, you know, and in this case, it is there is a barrier, so it is kind of displacement is kind of restricted along the barrier. And in this case, it is propagating both sides, restricted at one tip, propagation towards the barrier. Both sides it is restricted, and in this case, it is restricted with both tips convergence on the semi-elliptical form, and propagation of the barrier 30% of the all types. So fault displacement, linkage and evolution. So in this case, we can see that there is fault growth by radial propagation. So maximum displacement in one event, second, and then you have the third. So displacement along the fault can also vary. And in this case, we have these different A, B, C, D segments as isolated segments, and sometimes they can overlap and they can combine to become one fault. Like in case of Janori anticline in Punjab, we see this kind of a behavior. So the fault basically started to grow in, there are two different faults and they basically merged along the Sondun and they formed this Janori anticline. So we can have the linkages of the faults. Different type of faults. So in this case, again, displacement compensation along the multiple faults. So we have these multiple faults, they're interacting and we can have the throw, combined throw time. Again, these two faults are merging and then we can have the damage zone in between those two faults. And some of the geomorphic expressions of the strike slip faults, like in this case it is dextral and sinistrals, and I think everybody knows how we can calculate whether it is a dextral or sinistral fault, right? And along a strike slip, so these are the geomorphic expression of a strike slip fault. Like in this case we have a linear trough uh, commonly form along the principal displacement zone because structure blocks are slipped past each other along this zone, and because of the fracture material are more readily eroded along the fault zone. So in this case, if we have a strike slip fault, we can have sag ponds, we can have pressure ridges, we can have scarps, we can have deflected streams, we can have benches, and these are shutter ridge. So these are different features which we see when we see a strike slip fault. Because in Himalayas we have a lot of vegetation, and there is sometimes what happens is that the strike of that also creates an impression that there is some kind of a linear feature is going on, but most of the time these are just the bedding plane of the rock. So in Himalayas it is difficult sometimes to figure out or find the active fault or a expression of an active fault. So in that case we have to rely on different geomorphic markers. For example, sag ponds, if you have a chain of lot of these ponds which are in a linear pattern which are formed, and then we also take the help of remote sensing. Basically, in the afternoon, we will show you some cartosat images in which you can see in 3D. You can see the ground in 3D, and you can have a sense that one block is uplifted and other is down. And then you can trace out that fault along its length. Right? And then once you are convinced that yes, there are many geomorphic markers which are present along the trace of this fault, then you can decide that okay, if you want to go for field work, then you should know before that, which kind of features you want to see or observe in the field. It's not like you just go and then try to search because you want to optimize your time in the field. So this is we have very good, we have two examples very close to Chandigarh. One is the Sabilpur strike slip fault, and Taksal, Sabilpur, Taksal strike slip fault, and other is in the Saton region where you can see different stands of MBT which are behaving in a strike slip manner. So geomorphic expression of a strike slip fault, we can have sac ponds, and this is the fault and the scarp. So scarp basically means that you have some kind of a step-like feature, and when we are talking about scarps, we are not we don't want to consider river scarps because river scarps are formed because of erosion only. We want to understand that this is a tectonic scarp. So tectonic scarp is a step-like feature which is formed because of a displacement along a fault. So we are also looking for some scarps, and in remote sensing images, sometimes we can see the changes in elevation. Sometimes elevation changes are good, but sometimes they can be of the order of 1 meter or 2 meter, or less than that, or maybe 10 centimeter. So that we have to figure it out using remote sensing. We use remote sensing for that. We go in the field also. We use GPR, ground penetrating radar, in order to locate where is the fault in the ground, because most of the time maybe we are able to find the expression of the fault on the ground, but when we go in the field, in order to pinpoint the fault, we need a lot of techniques in order to see where is the fault. So geomorphic expression of a strike slip fault, when a ridge that has been translated along the fault subsequently blocks a drainage, it is termed a shutter ridge. And we have examples of this on the both the upstream and downstream side of a fault. River terraces may be systematically offset. If a strike slip fault is going through, let's say, a river terrace, you can see that these river terraces are shifted. A geomorphic expression of a strike slip fault, commonly streams crossing a strike slip fault will exit from a mountainous terrain into a gentler one. Scarps are also an indicator of a strike slip fault. On the downslope side of the strike slip faults, beheaded stream valleys may be preserved. A geological scarp, we can see that in this case, we have, some striations we can see on the fault scarp. Dip slip fault are inclined fractures where blocks have mostly shifted vertically. So geomorphic expression of normal or thrust fault, unpaired normal faults creating half grabens or half fault angle depressions occur more commonly. The down-topped hanging wall of a normal fault commonly generates a basin in which the sediments accumulate. Many normal faults bounded asymmetric ranges with one-step fault-bounded flank and a gentle sloping large to unfaulted opposite flank. Normal faults can omit the stratigraphy of the region and can push the older rocks on top and the younger to the bottom. Formation of a valley is also an indication of a normal faulting. Geomorphic expression of normal and thrust fault. Secondary synthetic dipping in the same direction with the similar sense of throw, or antithetic dipping in the opposite direction with an opposite sense of throw. Faults may be developed within a hanging wall block. Uh, in basically we are in the very close to the front. So here the Shivalik rocks, we can see that Shivalik rocks are thrusted on top of younger Indo-Gangetic plain. So in this, we have these different type of fault geometries. So now we are talking both of a fault and a fold, you know. So fault and a fold now both are occurring in the same place, and it is as sir has discussed these, shear zones. They are basically high temperature, but in our area here you can have a fault and a fold. So in this case, in the first example, this is a fault band fold. So the solid line represents the fault plane, and the rocks on top of the fault are making a fold. In most of the cases, they are making asymmetric kind of a fold. So second one is fault propagation fold, and third is the fault detachment fold. You can have the compression. So in this case, the fault is not coming up to the surface. In this case, the fault is somewhere down. So the fold is actually an expression maybe of a fault, you know. So beneath Chandigarh also there is a fault which we call as Piedmont fault. Maybe we can have some expression of that Piedmont fault in the you know southern side of the HFT. At some places we see the Piedmont fault, but in this region we have not seen any expression of that so far. So these are different type of fault and fold models. Basically, fault band fold model in which you can have the basically the layers are horizontal in this case, and then they are bent along that fault plane. Fault propagating folds, uh, different type of detachment folds. So basically in this area what we have learned is that you can have a fold, and below the fold, so now I will take some, for example, uh, the geomorphology of the Chandigarh region. So as I just discussed, that why don't we have floods in Chandigarh? So all of us know where the Sukna Lake is, right? And we have visited the Sukna Lake. So if you go to Sukna Lake, there are two types of mountains. First is the small one, and then you have the higher elevations. So these small ones are representing basically the Shivalik hills. And below that, you have lesser Himalayan rocks. Those are high in elevation. So Kasauli, we can see Kasauli, in a clear day from Sukna Lake. So the question is, one question is that what is when these formed? Why did they form? So we can think of the how this geomorphology, how this Chandigarh has come to its present configuration, geomorphic configuration. So this is a geological setup. Right here is Chandigarh, and skip it, चले गए नीचे. Okay. So right here is Chandigarh, and we have one river, Ghaggar River and Satluj River, and this is the Chandigarh anticline basically. And there is another anticline, Jhanori anticline, I was telling. So now you can think of that this Chandigarh anticline when these rocks came up, right? And there is a one more important thing is that there is HFT here, Himalayan frontal thrust is there. So as I just was telling that these are the younger rocks and these are the older rocks, as we can see in this image. So this is a cross section along this in a geological map. In that, what we are able to see is that Himalayan frontal thrust, it is northeast, and then you have a back thrust basically which is dipping towards south, and in between these two thrusts this Shivalik rocks are folded in this sense, making an anticline. And then you have other thrust, Sohn thrust, you have then Jwalamukhi thrust, then Baror, and then you have MBT. And if you drill in Chandigarh, if we see that only alluvial, and if you drill, we will find upper Shivalik rocks, and then you will have middle Shivalik and then lower Shivalik rocks. And this is again, you can see that. So now, if we see, like, Dehradun is here, Nahan is here, Chandigarh is here, and then anticline. So HFT is basically a fault which is going into the ground, and then these are shivalik rocks which are folded. Actually, it's making a kind of a anticline in this area. Okay. So there was a paper by Vimal Singh and Tandon. Basically, they explained that in this area, what so Chandigarh is right here now. Chandigarh, this is the Sukhna Lake, and these are the small mountains, the outermost Shivalik hills. So if we can think of that, if these mountains are not there, right, at one time, so the water from the sub Himalaya will directly come into Chandigarh. It will cause flooding. Will cause, if we go some years back, when uh, these rocks were not folded, you know, so there were some rivers which were directly coming through this anticline into the Chandigarh area. So these are just morphometric indices which are used to understand. I will just discuss the results. So this is again an important observation. There is one river, Ghaggar River, in which we have a lot of river terraces, and this is the Satluj River. So one important thing which we can think of is that there is you can see that this is around 300, and Ghaggar River is at a approximately higher elevation. Let's say 400, and this Chandigarh anticline, this segment is have a lot of these wind gaps also. You know, but in general, Chandigarh is somewhere here, right? So if we take a mean elevation somewhere, then we are at a higher elevation as compared to the Roped area. So what happened in this area? Basically because of compression, we have compressed the Shivalik rocks, and these Shivalik rocks are making this anticline. And Sukhna Lake is somewhere here, right? So these rocks are folded along a fault, basically. So this is this then this is the model basically which shows previously the all the water was coming directly into Chandigarh. Then there was an introduction of this thrust, Injore thrust, and then the introduction of HFT and Sirsa. And because of this, then you have folding of these rocks. So when these rocks are folded, then you have this outermost Shivalik. That is the formation of your Chandigarh anticline. So this is the model, right? Before that, the rivers used to come directly from the Kirtarpur fan into the Chandigarh region. And when these rocks are uplifted, now the rivers are deflected in the Pinjor, so they cannot directly come into Chandigarh, right? So this is a kind of a geomorphic evolution of Chandigarh. We can say that we have very good drainage pattern. The city is built good, but the planners who planned the location of Chandigarh, they were very smart people. They knew that Chandigarh is lying at a higher elevation as compared to others. So the water which comes from this drainage, it gets into the Ghaggar River, or either it is diverted towards the Satluj River, but it does not come to the directly to the Chandigarh. And tracks. There are tracks of the older river which used to flow. If you go in this top of this anticline, you will find sediments. You will find terraces which are present in this area. So if we date those, then also we can calculate what was the uplift of this anticline. What was the uplift of this anticline, because we know the height, so how it came up. So that can be dated. Okay. Any questions in this? So this was just the model given by the authors. So these rivers are coming, and there is another thing. Now this anticline does not just come in one day. It propagates. It basically grows in both the directions, east and west. So slowly this anticline started to grow, and then river started to deflect, and then this anticline is growing on the both sides, towards Ghaggar and towards Ropar. So this is the final, you know, uh, This is the present day configuration, you can say, of Chandigarh in terms of geomorphology, right? So these Shivalik hills are actually helping us, or saving us from floods. But on the other hand, you have a fault also beneath these. So that can cause a big earthquake, you know. So whether they are helping or not, that you have to think. So this is the reference, the paper from which this material is taken. So these are the slides I just took from Professor Alexander Storm. And sometimes we can have earthquakes, and earthquake can cause a rock slide, and that can again cause a long run out. You know. So in 2008, Venchua earthquake in Bichua in China, that caused a earthquake caused rock slide that caused a dammed lake. A dammed lake is formed, and because of that, you have outburst, flood, and then you have aggradation. So this town was destroyed because of a earthquake. So an earthquake can have these multiple chain of events where you can have, a landslide, a rock slide, a big rock slide, and maybe a dam is formed. And now this dam is breached, and now this water will go downstream and it will destroy various things. We know that in Himalaya, in India, Himalaya has the maximum seismicity, and we have a lot of dams here in Himalayas, right? And the second state where we have maximum seismicity is in Gujarat. So we need to understand that, how these faults are going to behave in future. So I just want to show these two slides. This is one of the best examples of large earthquake that produced surface faulting and triggered numerous landslides, including giant rock slides and rock avalanches. And this was in 2008 in Venchua earthquake. So you can see in this diagram that this is the fault, rivers ruptures, and these are the landslides. You know, earthquake induced landslides. So you can have a lot of these earthquake induced landslides also. So in this case, they are showing, this is the fault trace, and there is a 10-meter of rise, 10-meter of rise of the land after the earthquake. So you can see this, this whole building, is going up because of this earthquake activity. Okay, a little bit. I think I want to show some things here also. Yeah. So, yeah. So you can see that this is a figure from Jackson's. So you can see the epicenter earthquakes, right? So you have lot of earthquakes in the Himalayan belt, but in India, more or less earthquakes, and in Gujarat, some seismicity. But in general, you can think of that, the active deformation. Basically, active deformation means where you have today earthquakes. So those are the places where the earth is deforming in present times, right? So earthquakes shows us that where the earth is deforming in the present time. So in this figure, we can see that, you know, and there is another thing, because India is formed of various cratons, So cratons are again places where you have lower temperatures, lower heat flow, and in the oceans, basically, it's not that once your temperature is above 450 degrees C, then you don't have much earthquakes, because in oceanic crust is basically a homogeneous crust. But in case of continents, or in the continental landmass, the rocks are much more heterogeneous, and the concentration of uranium, thorium, and potassium, the heat producing elements, that is not uniformly distributed. So because of that, you can have different type of geotherms, and those geothermal gradients again basically can control the depths at which you can find these temperatures. So the temperatures can vary in the depth. So ultimately that will again control the depth of the earthquakes in the Himalayas. So basically, temperature again has a very big control on the depth of the earthquakes. Okay, so we have a active fault in. So I want to just show this. This area is very close to Chandigarh. This place is known as Khetparali, and there is a strike slip fault. This is Sabilpur fault, and the expression of this fault is it is displacing actually HFT here also. And this fault is basically, if you okay, you tell me what is the movement along this. Is it a right lateral or left lateral fault? If you see this, Shefali. Okay, so if boundary is displaced like this, right? So whether it is, yes, left lateral. Okay, good. So yes, we can see that this is an left lateral fault. So the Ghaggar River is somewhere here. And, so we see this very clear cut, evidence that this is a strike slip fault, and there are some streams which are deflected, and there is Nahan thrust, and MBT is also very close. So this area is very important, basically in terms of understanding. And there is also a landslide here in this area. There is a big landslide, and all that material of that landslide is deposited right here. We have not dated it, but if we date that material, we can correlate it with the event in the past. Because the landslide just happened here, and the material is just deposited at the toe of the landslide, which has not gone further away. So that kind of material can be dated, and it can be known that what kind of a event, maybe paleo event, has triggered that landslide. Okay. So there are some things to understand that yes, we have HFT which is dipping towards that side. We have a strike slip fault, and this strike slip fault actually we published a paper. There was a problem because on a now you see this is approximately 2 kilometers, approximately 2 or 1.5 kilometer of displacement along this strike slip fault. And geologically, and if we go in the field, we can see that the rocks are displaced actually. We can see the rocks are dipping towards north, and they are displaced. That is totally fine. Geologically, this fault is a left lateral. But we published one paper and we said this is a right lateral. Currently, it is right lateral. Because geomorphologically, the displacement of the streams and the features which we see in this area shows that there is some kind of a right lateral movement. But geologically, on a longer time scale, it is left lateral. So basically, in this case, what we have is we have upper Shivalik rocks; those are over thrusting, and the other important thing is that here there is a river. This river has cut 20 meters deep, and the fault section is exposed. So that is again an advantage for a geologist to go in the field and see this site. So the HFT, which is Himalayan frontal thrust, this is why I will say one of the best sites to go, and you can see that this fault is exposed. So right here what you see is that the fault is somewhere here, right? And the rocks behind that are making a anticline. you know I just showed you that then we can have a fault, and on top of that we can have a fold or an anticline canal structures. So and in this area we are able to see even 1 centimeter small folds, very very good folding basically in soft rocks. Generally, we think that a fold will form in a ductile or at a higher temperatures, but these are at very shallow in sediments. We can have folding also. So yes, so this is how it looks in the field. So this is a river terrace. On top of it, you have a river terrace. You also have a anticline. You can see this mudstone is going like this, and sandstone is also, and fault is somewhere here. You have fault, and this fault was discovered a long time back in 1985. This is one of the papers they have described these fault, basically this Khetrawali. And this Strikesleaf fault, you can see that it has different geological formations in this area. So the red is basically tetrode formation. You see this orange color? That is basically tetrode formation. So tetrode formation basically seeing the Pinjore formation right here. So geologically, you can see that different layers are, you know, placed along this fault. And the other important thing is that we have Nahan thrust and then we have main boundary thrust, which is within a distance of, let's say, 6 kilometer. Within 6 kilometer, you have these three main, thrust faults in a small distance. Now, uh, some things we are able to understand in this area, some things we are not able to understand. For example, here you have upper Shivalik rocks, but in between this contact, we have middle Shivalik rocks. And so this contact, here you have upper Shivalik, here again you have upper Shivalik, but in between you have middle Shivalik sandstones are popping up in this area, and they are making the contact. And this is Tikkartal region. This is Tikkartal, and in Tikkartal also there are so many active faults are present, and there are expressions of landslides. Looks like due to induced, maybe due to induced earthquakes. So this is how HFT looks like in the field. You can clearly see here that you have, uh, material or endoganglic plain material here, and this is petrot formation. These are basically clays, petrot formation. So the clays are overriding the older rocks. So these are like 2 million-year-old rocks, and these are very young rocks. They are thrusting on top of rocks. So this is how the HFT looks like on the on the right side of the river, and this is on the left side. So approximately 10 meter of this section is there where clearly you can see. Now the problem in these rocks in the upper Shivalik is that these rocks are very soft rocks. These are mostly clays, sandstone, so like that, especially the upper portion. And on top of that, you also have a capping rock in this area. So there are two river terraces, T2, T1, and they are paired river terraces. Both sides of the fault they are preserved actually. So these are paired river terraces. Now, uh, only in this area we find river terraces more or less here and one more T3 surface is there. So they are very close to the fault, right? But after that, you don't. The river basically starts meandering. Only here, close to the fault, the river makes a V valley. Clearly these river terraces are formed due to folding and activity along this fault, because only here we are having these river terraces. Once we cross HFT, then we don't see river terraces. Okay, these are some deformational. This is how the fault plane looks like. So you can see this deformational pattern. The soft rocks, basically these are clays, and I also saw silicon sites in very soft. Again, a picture of, and then this anticline is there, small. This is the core of the anticline, and we named it as Khetrawali anticline. Very small. You can see this folding here. These type of different deformational structures we find at, kind of shear sense indicators along the fault boundary. And this is a anticline, basically anticline which has retreated back, you know, because of erosion. Again, another site where a fault is present. So you can see boulder conglomerate formation on one side and cutout formation on the other side. So that is a clear-cut indication of a strike slip fault because along the strike, the rocks are changing. Okay. And in Google Earth also, you can clearly see, the topography. You can see that, this river was coming and suddenly start following the strike plane. And on the other side, it is totally different. And this fault is very clearly visible even on Google Earth. In the field, we were able to identify the fault. It looks something like this. Again, the fault, the strike slip fault. And what happen in this area? Once you go in the field, you will see some feature. Next year, rain will happen and it will erode the feature. So because it's a very fragile area, so next time you will not find this same feature which you see. It is better to take the data at that time. All plane. And there are some tilted deposits on top of that. Again, we are seeing some expression of a fault. Okay. Then we also do trenching. We make trenches, for a fault, and then we do extensive field work. We use GPR in the field in order to find where is the fault, and then we dig a trench. Trench is basically you make a big, uh, ditch into the ground, and then you want to see then where is the fault actually. You clean the walls of the trench, and now you can see that in this case, this layer is here and this one is here, so it's displaced. This is along this strike slip fault which I just showed you, the left lateral fault. The you know so in the Saton area, very there is a big landslide. Now I would like to to show some of the work which we have done in this area. This Saton landslide is actually looks like something like this. This road is going like this, and this whole material, this road is coming down every year, like 10 meters down. And civil engineers go there, they think, okay, we can do something. And they're trying to stabilize also. But when we went into this area is tectonically very active, I will say. And there are a lot of thrusts which are coming close, or even which they're crossing within this landslide. And this landslide is happening basically inside a lower Shivalik rock, a lower Shivalik sandstone. So this is a geological map. So in Chandigarh is somewhere here, and this Sotan is here. And one important thing I want to point out that there is a fault which is known as Yamuna Tier fault. Yamuna Tier fault. And a lot of people have marked it like this, and some people like this. And we were able to find that fault in the field, and we have made a trench on the fault, on Yamuna Tier fault. That fault also basically is an active fault, and it passes through this landslide body. So in this figure, you can see this is Ponta Sahib, Dehradun area. So Yamuna Tier fault is going somewhere here like this, and it is crossing this landslide, the Saton landslide from north south. And there are more faults which are coming east west. They are also going through this landslide. That is the reason. That is the only reason we have landslide only here. Along the whole strike of this road, we don't have landslide anywhere else. So why only at one place we have landslide? Because it has crushed and crumbled the rock from the both direction, from north south and from east west also. That is one point. And the second point is that uh, Yeah. The second point I want to make is this. So now this is the Saturn area. So there are one fault, MBT, MBF, DF, and there is a Sirmori Tal fault. Again, it is crossing. There is this Yamuna Tier fault. And if you see this whole area, if you see this whole zone is a kind of a paleo landslide site. Whole this sandstone is gone down because this is strike parallel, this is lower Shivalik. So within the paleo landslide site, only this small portion is active as a landslide. So when we are just looking on the road, we just think that this is the landslide. But actually the whole landslide is a bigger, is of a bigger size. And within that paleo landslide, only small portion is active. So we think that this bigger landslide happened might be due to a tectonic activity in the past. Okay. So you can see that this, there is this ridge kind of a curve, and we see these faults in this cross section clearly. We see this 10-meter cross section that these sediments are deformed and crushed. So wherever I went in Himalayas, most of the time I find that in faults we see we in landslides we see signature of some kind of a fault or a thrust zone most of the time. If you see inside the body of the landslide, if you search, okay. So yes, you can see, there is a lot of crushing and crumbling of the rocks. Okay. Now, I would like to show something. So I would like to show you some more examples where we are able to find the faults basically inside these. Uh, ये कैसे चल रहा है यार? Okay. So one more thing is that we made basically we worked in this whole area from Chandigarh to Kordwar, and we made geomorphic maps of this area, and we marked a lot of active faults in this area. So for doing that, we procured cartosat data from Indian Space Research Organization (ISRO), and then we are then using a software we can make a anaglyph. In anaglyph, basically we can see the 3D. We can have a 3D view of the area, and by doing that, we can see topographic changes, and then we can try to mark where the fault is going in the field actually. And using those, uh, then we are able to make these tectonic maps. So in Dehradun area, basically this fault is there, which is actually marked as a thrust. But at some places, we think that the northern side has gone down. And there are reports from Nepal also that MBT is showing that southern side has gone down. The northern side has gone down. So even though it is a thrust, it is showing that it is going the opposite way. So this is basically your main boundary thrust. And, some of the places it shows that maybe your northern side is going down, and we see these kind of signatures some places against on landslide. Yes, there is this zone deformation zone. Road has gone down 3 times. Then there is another landslide which is known as Umri landslide. In that landslide also, this is very close to Chandigarh. We again see this is the strike slip fault. There is a Umri landslide, a big landslide, approximately 1 or 2 kilometers. And at the toe of this landslide, we again see signatures of some strike slip fault, and also in the body of the landslide. So this is how it looks. The landslide is a big. This is Ghaggar River, and at the toe, landslide find signatures of faulting. You know, and here also we are able to see some normal faulting going on in the this landslide. This is how it looks in the field, and this is the joint data. So basically, when we are working with landslides, simply we can divide landslides into two categories, like either it's a rock or soil. If it is a rock, then it will have a lot of discontinuities, a lot of joints, lot of fractures. So when we go in the field, we take all the joint data. We try to take that all that joint data, and then we try to assess the slope stability of that area based on slope mass rating. In slope mass rating, basically we try to give a number from 0 to 100. If we are giving 100 marks, that means it's a strong, safe site. If we are giving less marks, that means it's poor quality or it can have destabilization, right? So it can be unsafe. So you can see that there is another then fault plane. We have drawn the fault plane which is crushing or crumbling this whole rock mass. So in engineering geology, when we say discontinuity, it includes any kind of a fracture, any kind of a joint, even fault, you know. So discontinuity includes everything basically. So this is again, in the field, this road was there, and then we were able to take the data of this, the fault which is present in the body of this landslide. Now this road is diverted because this road has gone down. It is diverted from the other side. Now this is a special case. In 2017 in Mandi in Himachal Pradesh, there was a big landslide. The name of the landslide is Katrupi landslide, and a lot of people have published a lot of papers in this area. You know what happened is there was a road, and suddenly during heavy rain, this whole rock mass collapsed, and the two buses gone down, and everybody died. So we also studied this landslide. So the important thing is that there are two salt mines. One is the other one is Gumma in this area. And in between, strike parallel, this is the location of the Katopi landslide. So this is the Katopi landslide, and this is the geology which was given by previous workers. So they have reported that there is salt in one of the formation, Ropri formation. Ropri formation is somewhere. This is known as Lokhan, which actually contains rock salt also. So this rock salt is proterogic in age, and we can see that this is the contact. So this contact is kind of a tectonic plate because these rocks are Precambrian and these are shivalics. You know. So when we went into the field, first time, uh, first of all, this is what we saw. That this is my student Abhishek, and we saw that there is a dome kind of a structure which is coming out of the landslide body. So you can see that within the landslide you have a volcano kind of a small crater, it's coming out, and these kind of structures are popping out of ground. So we think that there is a role of rock salt in triggering this landslide, because this landslide was a cyclic landslide. People have thought that every 20 years it starts to go down, you know. So we submitted the paper, and also along this landslide, I am able to find this limestone rock, which is a crushed rock, basically, which is MBT, you know. And I was able to see that this is the fault plane. I mean, it's going, and we were able to recognize that yes, on the right side of the landslide, we are able to see, because MBT is a older fault. So we are able to see that in the uh, now if you see this image, I have taken this image from a distance. So this is the dome basically in the center of this landslide, and this is the scale. Abhishek is going with GPR, and you can see this kind of a dome is coming up. Now this dome is covered by the sediment which are coming from the right side of the landslide, because now this dome is covered, but still it is rising. So what we have done is we have gone 3 years in this area, and we have done RTK survey in this area, and we are able to see that the rise is around 10 to 15 meters. 10 to 15 meters. a total rise from 5 to 6 years, you know. But this was, that is why it is very, very important when you are working in any area, you should always go in the field. You can do remote sensing, no problem. But that's just a tool. Just don't just rely on remote sensing. You need to go at the site. You have to check the site. You have to see everything. So this is the RTK survey. You can see that in RTK, you can see the uplifted zone within the landslide. Again, these are different surveys of the dome body which were done in 2018, 2022, 2024. So again, this landslide, the dome we have, this is the rise. It is not like everywhere it is rising. Some places it is rising more, somewhere less. And then rain is coming, and it is, again some erosion is going on. So everything is going on in this. So we propose that causative factors, salt tectonics, fault, and rainfall. Previously, people said the maybe this landslide is triggered because of a just because of rainfall, or they might have just said that it is a seismic event or something. But we have added that basically what happened, a lot of rainfall happened, water percolated down, and the salt became more and more beyond, and then it pushed through the fault plane of MBT, and then it toppled the rock above. And that is the reason, so salt tectonics, fault, rainfall, everything played the role basically in triggering this landslide. Another example from Uttarakhand. In 2018, we worked, one of my student did the PhD here. So basically, this is a Kalyasol landslide. So in this, we see this is a hard quartzite rock, very hard quartzite rock. And uh, you always have some landslide happening here, a lot of problems. So there are two things which we discovered in the field when we did field work here. First was that it's a plunging fold. It's a plunging fold, and it's basically plunging towards the road. It's like this. And always small, small chips are coming onto the road because of, wind and other things. That is one thing we discovered. And the other thing which we understood from the literature, that there is a fault. The name of the fault is a Kalyasar fault, and it passes through this region. And you know, we saw that wherever this fault is passing through, the rock is totally crushed and crumbled. But other places, you know that quartzite is a very hard rock. If you hit with a hammer, hammer will bounce back. But only at this place, by hand, we are able to take out chips of quartzite of 1 centimeter only, by hand, because it's so crushed and crumbled. And again, the role of a fault. So along the road, this is a big landslide. There are more than 400 papers written on this landslide only. More than 200 papers. So where we see landslide, here again we see landslide, and this place is very important, number 3, because here what happened is that, so Parvesh is standing, uh, you know, so you see this quartzite is coming, dipping like this, and here it is totally crumbled. It started raining that time, and the water become milky. It is so crumbled and crushed. You can see that this is hard. Quartzite is coming, and here you have this crushed rock mass. And there is a contact, actually. There is, I think, basalt on this side. So we are not sure that whether, because I mean I think it is because of the, I will say that it is because of the fault, some past activity. So you can see what a fault can do. It can crush a rock like a powder. So that is the observation from this landslide. Yeah, in 2015, this is basically, now we are going to Manikaran in Himachal Pradesh. So in 2015, there is a place known as Manikaran where hot geothermal fluids are coming out of ground. So there is a Gurdwara and a temple there where people go for worship. And 2015, there was a big boulder. Big boulder came, and it came and destroyed the building. This is basically the hot. This is a hot pool here. You can do swimming in this hot pool. So basically, we got a project from Department of Science and Technology, and we installed some sensors. First of all, the problem was to find out the place from where this boulder started actually. So elevations are very high here. You can see the rockfall started from some place here, and it bounced and it hit the Gurdwara down. And we did a lot of field work in this area, and you can see my student is standing. The size of these rock blocks is very big, and then we were able to find the site. A lot of debris is fallen there. There are a lot of unstable blocks. So the idea was to install a landslide early warning sensors at this place. So we did field work, we did drone survey in this area, made a lot of maps, and so we installed some sensors, crack meters and tilt meters. So we installed in this area, and we have 1 year of data of this. So the data is coming through into to our workstation in the department, and we have 1 year of data in which we can see these rock blocks are tilting or things like that. You know, so installation was what not very easy. So we uh, have two ropes, one for safety and other is like rock climbing ropes. When we have the engineer and he has to drill actually inside, and also the mountain lion I think in the night comes in this area, and my student was camping here for 10 days, 10 to 15 days. So this is the data which we got from the sensors. This we will publish. Okay. Yeah. Any questions? Any this? Okay. I will show one paper which was published in 2023. So this is basically this is the area where we were working, and HFT is here. Mostly our work is concentrated along HFT MBT, but mostly the active fault is concentrated more along the front. So you can see Chandigarh here. Chandigarh is right here, and there is this strike slip fault. I was just telling the left lateral, right lateral. So this fault is going like this. Okay. And one more thing, if you see in Punjab, this Janori anticline, this anticline propagated from this direction, and this one propagated from and this area is uplifted in between, and you will find sediments of Satluj River when it was flowing from this area. So in Punjab also, the tectonics played a role in creating the Janori anticline. And if you see the Beas River was flowing from this area. But because of the propagation of this anticline, this area is uplifted. So because of that, this river is shifting like this. So it has to make a long turn because the land is slowly rising. So I will say the Planck model in which the topography slowly rises is more applicable, I will say, in this area, because it's not just a sudden uplift of the topography. And then you have a lot of these drainages, your drainages are formed, and then you have these drainage density. In that, you can do morphotectonics. Basically, you can find some anomalies, some drainage is deflecting, things like that, in order to understand if whether there is a fault or some activity. That kind of exercises we will do in the afternoon, basically on. You can do it on computer, but we have made exercises so that everybody can do it on paper. So morphometric indices you can calculate. Okay. So, so basically, there is a very important. This Chandigarh is here. There is again this big fault, and it is going up to Dehradun. And this is basically the Katropi landslide. This area also we are working, and in the whole this area basically we are working. So for doing this study, this is the cartosat data. So you can see Chandigarh is here, the river. This is the fault I just showed you. And in the cartosat data, you can mark the trace of the fault. You can actually pick the trace of the fault, where the fault is on the ground. And then you can go. So these are like scarps. Scarps are like, some tectonic scarps. So the surface is shifted. And then you can try to date. You can go in the field, you can take measurements, and then you can try to date the sediments in order to understand when this deformation happened. Okay. So you can see this is Chandigarh, Sukhna Lake, HFT, and then this is Pinjore Garden. And there is again in 1600 there was a big earthquake which caused the step which is formed in the Pinjore Garden. You see this waterfall is there. So that is because of this earthquake activity in 1600s. That was just made a waterfall. Okay, and this is the geomorphic map of the same area. So you can see these different river terraces along Ghaggar River. 5 river terraces I was just telling you. So the Mansa Devi temple is also on a river terrace. So the river actually Ghaggar used to flow from this to it shifted, actually migrated from, right. And you have HFT. So along HFT you have uplift, and because of that you are forming these river terraces, and the river is also shifting onto the lateral migration of the Ghaggar River. So this side you don't have much. So these are basically representing unpaired river terraces. So in this area, basically in Thapli we put the trench. A trench was made. So this is again cartosat data. In cartosat data, you can see in 3D, and you can if you put glasses, we will show in the afternoon. Students will show some cartosat images in which you can see uh, perception, and then you can mark the different fault traces. And you can see this sag pond is forming shutter of ridge, and then the traces are coming of the fault. Now we know that the fault is going, but in this area, where to put the trench is a tricky job, even though you know the fault is there. But on the ground, to pinpoint where the fault is going, because sometimes we dig trenches, but we don't find anything. So that also happens. Sometimes, some failures also happen because, it is not like that you will always put a trench and you will find the fault. Some deformation, river shifting, and then some RTK data. This area was, mapped. Now this is how this fault looks in the river section. So we are looking towards north, and the fault is actually going north south. So you can see this is the damage zone. This side has gone up, this side has gone down, and there is a sandstone, lower Shivalik sandstone. Now this fault is actually an active fault. You know, very close to the active fault, you have sandstone and some deformation in the sandstone. But this side you have lower Shivalik rocks. These are basically clays, mudstone, very soft rocks. And the other important thing which we discussed is that we have quaternary deposits on the top, right? So we need these deposits. Need these deposits because we want to date this. Because these rocks, the age of these rocks is like 18 million or something. But we know from the definition of active fault, we need to have some sediments which are around 10,000 or 1 lakh, something like that, right? But 18 million rock, 18 18 million old rock, if it has displacement and it does not have any sediments on top, then you cannot tell that it's an active fault or something. So you need to have some quaternary deposits, right? So, so this is the river section. So, the fault is coming like this. So these are fields actually. So this field is this step is formed because of the fault. Actually, it is not human-made, terrace forming. No, it is actually fault is passing through this area. and we have done GPS profile, local station, and then we have to convince the farmers that we will put a trench here and we will, they have to be taken into confidence. So GPR, then we are able to make the trench dates, you know, and this is the interpretation like how this. So the three events were reported from this trench. So in this paper, it was so this fault is basically shown as a stream partitioning in this area, and this portion is logged. This portion is and this portion is basically creeping behind that. So it was shown that this area is strain is partitioned along this boundary. That is what is proposed in this paper. Okay. Okay, sir. I think I finished everything. Thank you. Okay. Yeah. If you have any questions, you can ask or discuss. Want to discuss something? Yes. Yeah. So one thing I think I want to say that when we collect this joint data in the field, so you can see this rock is dipping, and there are a lot of joints, and then those joints are used to do kinematic analysis in order to understand whether what type of rock failure can happen at that. So like we classify planar failure, wedge failure, toppling failure. And then some of this geotechnical data is you can put into a software and you can try to see that slope configuration, whether it can fail or not. So that kind of thing we can do when we go in the field. And no doubt we also look for some kind of geomorphic markers which can tell us that whether some kind of a fault is present or not. Because if you see this rock, it is not easy to understand that there is a fault is passing. So sometimes you have to see away from that side, not just at the landslide. You have to see a bigger view. You need to take a bigger view into picture, and you need to think that how this slope is different or anomalous from the other slopes, right? So in this case, we are showing the fault is there. This turning is there. So this thing you can do stereographic projections of kinematic analysis of different joint set data. You can show what type of joint failure will happen, and based on that you can again discuss that what kind of remedial measures you can provide to the slope. So this is what is a primarily step, and then you can collect more joint data, and then you can try to do some kind of a modeling, that you can do in rock science software. Okay. So I can show you some more work which we have done. Previously, HFT, previously, this is again one paper we have published. In this area, we were thinking HFT is a blind fault. Blind fault means it has not come up to the surface. But when we did field work, we were able to see that, fault is actually coming up to the surface, and it is also making the anticline in the Tripurali area. These are different river terraces. As I was just showing you that you need to also have some different river terraces, and then dating of these rocks. So now, Ishmit, your answer to your question that you see my student is hanging there with a rock climbing rope and he's taking muscle samples. But this need to be done in a very safe manner. We had a lot of safety gear here. You cannot just do it by yourself. You need some teamwork. So this was the model which was given that, first the deposition and then some truncation in this area due to this fault. Yeah, this also I want to show. Now this area, basically this is Ganga River and this is east of Ganga River. This is Kordwar area. And in this area, uh, HFT is somewhere here. You can see HFT here, right? So now I was telling about a blind thrust or a Piedmont fault, a fault which can come ahead of HFT in the southern portion. So there is a river. This is known as Malin River, and this is Indo-Gangetic Plain. Now, this in this area you will not find much geological features. So we did some morphometric analysis in this area, and if you see this diagram very carefully, you will be able to see that there are some drainages which are formed in this area. New drainages are coming up. So we proposed that HFTs, but in this area, a fault is reported, you know, which is going beneath these sediments. And this area is being uplifted slowly. So if any area is being uplifted slowly, then in that area you will have new drainages are formed in that area. That is because water is the first. If you tilt the surface, the water will know. Okay, it will not go, it will go the down. So in this area, these new drainages are formed, and there is also deflection of this river which was coming. So it was coming like this, and now it is deflected. So using these two evidences and also some photographs, we were able to show that in this area, there is upliftment, and the fault is passing somewhere here. This fault is known as Najibabad fault in this area. So morphometry sometimes can be used to see or understand areas where we have no information. Okay. Okay, I think that's it for now. I went very quickly because I wanted to cover some things. Thank you. Sir, I think the data is with the uh, we don't have that kind of a coverage, but yes, small earthquakes, but the most of the data is controlled by National Geophysical Research Laboratory and some of the sensors, Wadia, and then uh, that is National Seismological Center. So they have, but we don't have actually. Yeah, but once I went to one place in Dehradun, uh, people, I have those figures. In one area, the river actually uplifted two times along the fault, and people visit every year there, thinking that some supernatural power is there. So the area actually lifted like this along the river. Some stresses are maybe released or something. But this is very important. Yes, your point. I also think that we should have some kind of a network which can observe where these earthquakes are happening. Any question? Oh, I think so. Then we can stop. Okay. Thank you. हेलो। एक मिनट, विवेक, अभी इस पे यार इंटरनेट ऑन कर दियो अगर हो सकता है तो। हो जाएगा मेरे इस पे कंप्यूटर पे। एक मिनट है ना, इस पे इंटरनेट हो जाएगा ऑन क्या बाई चांस लॉग इन करके, जब वैसे ही हो जाएगा तो कर देते हैं फिर, क्योंकि मैं फिर गूगल अर्थ से भी दिखाऊंगा कुछ कुछ ना चीज़ें। देखना यार जरा, नहीं तो मैं फ़ोन से लगा दूँ। हो जाएगा तो बढ़िया है, फिर गूगल अर्थ को मैं दिखा सकता हूँ। नहीं, तेरा है तो तू डाल दे तेरे को। हेलो। नहीं चल तो रहा है। 5 शेफाली, वो जो फिगर्स है ना वो दो कंप्यूटर्स में डाल लेना, जैसे दो लैपटॉप में, है ना। फिर वो उस क्लासेस वगैरह बाद में करेंगे, अभी अभी 1.5 आवर लेक्चर होगा, उसके बाद फिर हम प्रैक्टिकल करेंगे, ठीक है। हैं? चलो ठीक है ठीक है ठीक है, मैं फिर इसमें फिर कौन सा वाला? मेरा मेरा मैं अपना ही करता हूँ। Hello. So in this session, we will do a morphometric exercise, and we will also discuss what is morphometry. Quantitative measurements and mathematical analysis of Earth surface forms. So as you can see that there are different drainages like dendritic, radial, vallus, rectangular, and irregular. So we need some kind of a measurement in order to understand how these drainage patterns are affected, and how it is uh, are they, I mean, just controlled by structural, or is there any tonic control? So what is morphometry? Morphometry provides an objective framework to describe landforms, geometry using measurable parameters like length, area, slope, relief, and network topology. Unlike qualitative description, morphometry relies on numerical indices enabling scientifically reproducible comparisons across basins, regions, and tectonic settings. The morphology of a basin is a cumulative product of climate-driven erosion, fluvial incision, weathering, tectonic uplift, and lithological resistance over time. Morphometric indices encode valuable information about landscape evolution, hydrological behavior, and tectonic activity. So applications across earth sciences, tectonic geomorphology, mountain front sinuosity, right? We will discuss that in detail. And then valley flow ratios, stream gradient indices, and asymmetry factor in for neotectonic deformation and active faulting. Okay. And in engineering geology aids suitable assessment for dams, reservoirs, and infrastructure projects through terrain analysis. So it's very important. that we do these kind of analysis. For example, if we are building a dam, right? So whether there is a active fault in that area close to the dam, if there is a active fault and the reoccurrence interval of that active fault is around, let's say, 50 years. So within 50 years, this there will be an earthquake in that area. So if we are not taking care of that fault, then that dam can be destroyed by that activity. So it is very important when we are doing these engineering uh, assessments that we understand or we explore that area through remote sensing, through field work, and through literature also to understand if there is any active fault. In hydrogeology and watershed management, guides flood modeling, runoff estimation, soil erosion studies, watershed prioritization for resource management, environmental and climate studies, basin shape, relief influence, sediment flux, peak discharge patterns, and landscape sensitivity to change. So, morphometry translates the form of landscape into quantifiable matrices that reveal its function, history, and dynamics. By measuring Earth's surface geometry, morphometry provides a powerful lens to understand the processes that have shaped and continue to shape our planet's dynamic landscape. So, for example, I can just show you some examples or some questions. So, if we see the drainages which are formed around Chandigarh, we can see some drainages which are formed on Chandigarh anticline. Even though these rocks are shivalik rocks, we can try to identify. Uh, पूछना जरा उनसे कैसे ये गूगल अर्थ कैसे आएगा इस पे. My screen is not projected here. I want to show this screen on there. नहीं आ रहा. Only PPT. PPT से मिनिमाइज करूं क्या? नहीं नहीं. अच्छा, मैं एक बार इसको मिनिमाइज करूं प्रेजेंटेशन को. क्या पता उससे आ जाए. हम्म. किस चीज के? हम्म. मैं तो भी लेक्चर ले रहा हूँ यार. हाँ हाँ, दिखाना किसी मेरे इन्होंने किसने भेजा आपको? Now, if we just see some of these drainages, for example, in this area, if we zoom, so you are looking at this drainage now. you know, this one. You see this drainage? So the question we can ask, why it is like this? Why the shape of this drainage is like this? What is controlling that? Because these drainages, they are formed like, and we can again see the drainages which are formed on top of, which are formed on top of the Chandigarh anticline. And there are paper written where people have shown that there are some deflections of the drainages, and because of that, they are trying to identify or mark some active faults in this area. So sometimes these drainages and the water pattern flow can also influence how these drainages are built. Okay. So we need some kind of a function, some kind of a tool in which we can quantify these values. Stream order, understanding drainage network hierarchy. Stream order is a hierarchical method of classifying drainage network components according to their relative position and branching complexity. The most widely accepted system is Taller's stream order, which assigns numerical orders to stream segments based on tributary arrangement. Stream order is a fundamental parameter in morphometric analysis because it provides a structural way to quantify the drainage network's organization, branching pattern, hydrological behavior. This classification system forms the fundamental for understanding how water moves through the landscape. So the first order streams, the smallest channel with no tributary, usually originating in a waterhead region. So that will form the first order stream. Second order stream, when two first order streams join the channel downstream, becomes a second order stream. Third order progression, when two streams of the same order merge the downstream segment, takes the next higher order, that is the third order. And then following, when a lower stream joins a higher order stream, the order remains unchanged. Okay. So this process continues throughout the basin until the main trunk stream reaches the higher order, creating a complete hierarchical network. So as I was showing you in the morning, if there is a drainage basin and there is a fault, we have seen that thing in a Hitparali region. That we have if some active fault is there, and if it is seeing the uh, main channel, the trunk channel, then the erosion is in the because here in Shivaliks we have soft rocks, right? So erosion progressively you can see that it is going slowly and slowly upward. It is causing a headward erosion. So in a way, what we can see is that, so for example, like in what we saw in Khetpali, so these are the mountains, let's say, and there is some river, some tributaries are coming like this, and uh, you know let's say there is some kind of a fault or something, and because of that some displacement is there. So the erosion, because in this area the rocks are very soft, uh, upper Shivalik rocks, they don't have any cementing material. So what is happening if the river is going like this and somehow there is some change in this, then what will happen because of this erosion? Now the erosion will start happening like this, right? This stream, when there will be change in gradient here, now the erosion will start happening. Now this stream is able to see that yes, there is some change in this basin, and now the erosion will start to happen in this area. So similarly, this outward erosion will start propagating upward into the drainage basin. And we are able to see that very clearly in the field that now one thing is there because this stream is getting lot of water and there is less stream power in the smaller stream. So the amount of erosion will be more in this one as compared to this one because here you have more stream power, so you are able to erode more in the main main channel. But in tributaries or in the small, you have lesser erosion. And we have also seen that when this erosional front will progress towards the uh, higher reaches, it will then cause some kind of a small landsliding event here. Now this whole basin now starting to erode, and it will go to a the if the starting the basin was like this elevation wise, this is basically elevation, let's say, with length. So slowly it will, because of erosion, the river wants to bring it to a kind of a base level. And our idea is to, uh, the water is falling, the rain is happening in the drainage basin. Our idea is to quantify with some numbers whether this is tectonically driven or it is just simple erosion is happening. Okay. And there are many basins. Let's say there is a fault. Let's say there is there is a drainage basin, and if one fault comes along this, and it let's say it displaces something like this. So what will happen? This basin will become little bit like it will be displaced. So it will be something, you will see that this corner is here and it is displaced along this fault movement. You know. So if a strike-slip fault, let's say there is a fault and it is cutting through the basin, because these basins they are formed due to long-term erosion, right? Long-term erosion is happening and water is falling. Now there are other factors which are controlling the how this drainage network will form. The other factors are like the strength of the rocks. If the rocks are very strong, for example, let's say you have a strong sandstone or other metamorphic rocks, then the erosion will will depend upon the strength of the rocks. But especially in upper Shivalik rocks, where we have these mountain, these anticlines, there it is more or less topography driven, and you can have some kind of anomalies. And in Himalaya, we see these kind of truncation of some drainage basins because of active faults. So if a fault is crossing a basin, so you can think in your mind that the basin was forming like this, but now it has displaced. And especially where you have stronger rocks, there you can preserve this kind of a anomaly for longer time scale. But if the rocks are weak, then this will again merge with this, and then maybe we will not see that displacement. Okay. So one thing is that, and there are other things that basin can be tilted. The river might shift this side or that side. So those kind of things can also happen in the basin. And if you see basins in Manikaran region, if in Manikaran, if you see basins, you can see that those basins are very heavily, the rocks are very strong. And you can even see that in those cases, you can have a leaf-like pattern. The basin is something like this, the drainage network in the Manikaran area. So now in this case, if we see a basin like this, what is controlling that? Why it is forming very clearly like this? So, you know, I can just show it on this. So now I will show you some other example in which you see a basin and you will just see this same thing. It's okay. You see this, you see this part. Now we are looking, this is basically Manikaran, right? And if you see this, this basin, this one, you see it's like a leaf, right? So the other thing, even though there is long-term evolution of these basins, so I think that this is controlled by joints, and in the rock mass you have different sets of joints. So depending upon which joint is more resistant, you know, so weathering will happen according to that. So you can see that this is a beautiful, basin with this kind of a pattern. So the point is, yes, the rocks are hard here, no doubt, compared to Shivaliks, but you can see clearly a very good, shape. The other thing which we can see in terms of geomorphology here in this area, you know, we can see a lot of villages and for example, like let's say this one, this basin, you know, this one. So do you think it is just simple erosion? Erosion has formed this basin, or there are some other processes like geomorphic drivers which can make a basin like this? Yes, any guesses? In the morning we discussed what are various geomorphic drivers which can change. Okay, so you can see now. I think this is Vyas River. Vyas River is flowing in this area. So you can see that there are some villages here. This village is here. So in hilly terrains, villages are generally where you have some kind of a soil cover, right? So from where this soil is coming, glacier, right? So yes, we discussed in the morning that there are three main drivers. So basically, right now you are not seeing the glacier, but in the old times when glaciation was there, these areas might be covered by glaciers, and glacier do lot of grinding, and that grinding basically produces these shapes, and then you will have soil on on the higher reaches of the mountain. So now the point is that maybe some of these drainage basins, not today, but previously they were carved by the glaciers, by the movement of glaciers. Now we are maybe not seeing them, right? So if you see the topography of Himachal, right, you will see a lot of areas. Like you can see that okay, there was a glacier. There are other factors also, no doubt about it. Now if we see this valley, this one, so you can think of okay, this valley was coming, and you will be able to see you if I just zoom in this area. Let's see, you know you can think of that okay, when glacier was coming, it was coming, and you can see some kind of a blockage here. You see this, this now this is a kind of a anomaly in a drainage basin. So if I'm looking it like this, now my mind will start thinking okay, maybe some fault is doing this, because if this is a drainage, it should have, this side will be, should have been on that side, right? It is just blocking the way. You see, if this rock is like this, and then you know so if you just search in, you will find many areas where you will have U-shaped valleys which are not connecting with the river. You have U-shaped hanging valleys from where the glacier just falls down. So the idea is, even though today we are not looking at glaciers which are covering all over the Himalaya, but if we go 1 million year back, glacial, interglacial periods, then this area was covered by glaciers. As we can see today, these you can see these areas. You have lot of this, and you can see how it is formed. So if we are thinking in a longer term scale, you know, uh, then wherever you have rivers, maybe at previous times the glaciers were flowing there. and you will find a lot of sediments in Himalaya where you have fluvio-glacial. Fluvio-glacial means they are derived from glacier also and from river flow also. In the rivers, the pebble will be more rounded, in glaciers will be more angular, unsorted. In river, you have sorting of uh, sediments, right? So, so now you can see this is the Byas, right? Byas is starting from somewhere here. So this whole valley, this Kulu Valley, So previous time maybe the glacier was flowing here, but when they retreated, now this became a river, a perennial river. And same is the problem of Joshimath. In Joshimath also now there is a concept of north and south slope also. You know, the slopes which are facing the sun. You know, so these slopes the ice will melt, but the other side you will have vegetation, trees, and everything, right? And you will have more or more soil formation on the southern slope. So the population will always sit on these slopes. For example, Rekong PO is also, a area where you have subsidence going on. But the point is from where this soil came. It was not of a fluvial origin. It was a origin of a glacier because glaciers have grinded and produced that soil. Now we have made houses there, and now those areas are sinking. So sometimes these landslides are caused by some kind of, geomorphological. These are due to some geomorphological features which on which we are building houses. So same thing is happening in Joshimath. Joshimath also, where we have this subsidence going on, all that soil, you can even see a shoot of glacier coming down, and that area is now sinking. And this is a big problem in Himalayas because with the rainfall, every year we are losing a lot of soil. And a population can sustain on top of a soil. If you have rock, you cannot do anything. So this is a big challenge for these Himalayan states. So now we have this concept, right? Now we understand that okay, these rocks, they might have seen lot of glacial and interglacial periods, right? Because these are very old rocks. But yes, you can see signatures of different rocks on top of this. So now if let's say we see a active fault which is cross cutting this. Now you see this, in this we are seeing a lot of these linear features, but they might be bedding of which is just cut by the erosion, and it looks like a small linear pattern. Okay, so if we want to find a fault, so I can just show you here one example of a fault. So now you see this drainage. This side you have a drainage divide, but on this side you have a drainage divide and again drainage divide. So this in between, what is happening? So actually there is a strike fault which is moving in this zone, and it is making a backhill facing scarp. Let's say the mountain is like this, and there is a fault which is a thrust, so it can do something like this, and so it will look like this because the fault maybe has moved this side up, this side down. Let's say now this is known as backhill facing scarp. Backhill, this scarp, this fault scarp is facing backhill. you know so we see some kind of a feature like this in a mountain. That means a fault maybe is passing through that. And we see a lot of areas, especially where this kind of backhill facing scarp is formed in the terrain. Now what happens is the fault is formed. Let's say we don't have any datable material. So what people have done is like you will have rainfall, some erosion, slowly, slowly a sag pond will form here. And then you will have sedimentation. So now in this sag pond, you will have layers of sediments. So we can do drilling, take out these samples, and these can be dated. So when we date that, we know the age of the formation of this sag pond. Approximately, then we can put some constraints when this fault was active. Because in the sand, in the soil, we will find quartz, and quartz we can put in a machine and we can calculate its age. Okay. So yes, so this is again, you can see this active fault is passing through. Now this is Renuka Lake in Himachal. You can see this is Renuka Lake. Uh, and this Giri River used to flow from this side, like this. And there was some tectonic event. And because of that, now this river has shifted to this side. But previously, it used to flow from this direction, like this. So a tectonic event can uplift any area and change the course of the river also. What are the geomorphic markers? We see this very steep scarp here also, and there are some traces, linear traces of this old displacement, which are still you can follow across many ranges. You can see some kind of a displacement features which are present in this area. So the point is there are many factors which are shaping these older drainage basins. Their lithology is controlling. Some of the drainage basins have seen lot of glacier interglacial periods. Maybe they have seen some earthquakes also. And maybe a fault is passing through them. So all these factors might have contributed in the formation of these drainage basins. Somewhere some factor is more, somewhere some factor is less. Okay. Now, if you look here, there is a valley on top of a mountain. There is a valley which is formed on top of a mountain. So you can ask, what was the origin of this? I also don't know, but these are kind of things, This valley is formed on top of a mountain. On top of a mountain, you have a valley. What is controlling that? Whether it's a fault, maybe paleo fault or something. So there are so many anomalies which you which are there in the field, and we can try to understand them. And sometimes when you have landslides, you know, uh, because of that landslide, if let's say there is a big this basin is there, some landslide happens. Sometimes rock avalanches, in a rock avalanche, what will happen? All the rock maybe fall, and it will make a deposit, you know, some kind of a deposit in front of this. So this is maybe a rock avalanche, so it will have a lot of uh, material which is just in front of this. And sometimes this can cause damming, damming. And it can break suddenly and cause a lot of disaster. And we saw these basically in Kyrgyzstan. Lot of these. damming, basically damming by paleo earthquakes. So paleo earthquake caused a lot of damming, and lot of these rock avalanches are in front of the in the drainage basin. And somehow, if the lot of rainfall or something happens, they are triggered, and they can break any dam or things like that. And there are features in Himalayas also, which are present like this. There are a lot of places where you will see rock avalanches. Rock avalanche is basically, it's a kind of a paleo landslide, which all the material is just lying nearby in drainage basin, and it has not been remobilized, because the size of these rock avalanches can be very dangerous. If there is a dam downstream, lot of debris and rock comes, it can destroy that. So we need to also understand or map these kind of rock avalanches or these kind of debris material, which sometimes the problem is that sometimes we think that these are just glacial born moraines, because it is, sometimes tough, because moraines, yes, moraines are the product of glacial movement, no problem. But sometimes if we have paleo earthquakes, they can also make these rock avalanches, right? So, and we have found some rock avalanches in Uttarakhand. We, you know, we have found those sites, and we are working on those sites, that if they can get mobilized, they can cause a lot of damage downstream. You know, so now you are understanding that, okay, a drainage basin forms slowly and slowly with time. You know, it will have some kind of parameters. But if that drainage basin is deflected or changed, some anomaly happens, then our eye setting should be like that, that yes, we should be able to recognize, okay, there is something is happening, this fault is passing, let's say 5, 10, or 20 kilometers. Because if you have a drainage or a drainage divide, you have rainfall, so this drainage divide will slowly degrade. you know if something is happening in this or this basin, yes, we are thinking, okay, some tectonics is going on, maybe it is not just pure erosion, right? because we are because erosion will always happen, no problem. Erosion will always, whenever you have rain, you have some kind of erosion is going on. But tectonic is just instantaneously, a tectonic driver, which is changing the shape of our basin. Okay. So when I see any area, I try to figure out how this has formed. What is the anomalous thing here? Is it normal or is it behaving abnormal? So all these things you have to keep in your mind, because when we are just, today I'm going in the field, I'm looking at a surface or a mountain, I'm thinking, oh, glacier is not there or something, but it has all those effects incorporated into the terrain. So let me show you one more example where you can clearly see a fault. This is of course a paleo fault. Yes. So now, yeah, this is this. Yes. Okay. Now you, all of you, try to observe. Do you see any anomalous thing in this figure? Anybody? Sarabjit? Center of the river. Here, there is something. This, yes. Okay. Anita, Sumit, anything? Uh, you can take your time. Little bit time you can take. Try to see something anomalous in this. Arnav, are you able to? Can you identify something anomalous in this figure? Okay. Maybe something going north-south or something going east-west. East-west? Where? Where? Or this one? North-south also? Where? You can show me. Yeah. Which one? You can point it out. Yeah. Okay. Yeah. So now, yes, Anita, yes, she is right in telling that there is something, there is something going, and this is a trace of. Okay. So let me show you very interesting feature here. So this is a paleo fracture, or you can say fault plane. Whether it's active or not, we cannot comment on that right now. But yes, there is a Sirmaur Degree College. Is right here. There is a college which is built on top of fault plane. Because what happens in mountainous areas, you have a slope like this, right? Wherever you have some kind of this, so you get some kind of space. So the college is built on top of that. I think it's buffering. The picture will become more clear. Is it clear now? Okay. So now you see this fault plane. You can clearly see this fault plane, and right here is the college. So these and now the important thing is that this fault fracture is continuous approximately 50, 60 kilometers. It is not just at one place. It is cutting across all the mountains. And I will say, you can see that, you are able to see the fault trace, so somewhere here it is going like this. And we will also show you in the practical session, we will show you some cartoset images in which anaglyph, you can see an anaglyph, and then you can have a depth perception how a fault can be seen in 3D. It's like, aerial photography where you are just flying from top and you're looking down. So now one more thing I will say about this. What do you think? This drainage basin is okay? This has evolved right, or something anomalous for this drainage basin? The sea like that. Anything anomalous? We can see, yes, there is a fault in its, oh, kind of. This basin, let's say observe this basin. To me, it's little bit anomalous. And why it is anomalous? Because this side is okay, we are eroding. Now, this side also we are eroding, but this mass has somehow come up into the drainage basin. So I will say that this is anomalous, because if it is, you know, both sides should have been similar, but this side is coming. You can see that it is coming into the basin, and the fault is also. We can see the fault trace also, right? This drainage basin, is there any anomalous thing in this drainage basin? Do you see anything anomalous basin which is right above this one? So now if we think in terms of, okay, erosion is happening and it is merging into this. I will say something is passing here. Why? Because right here there is a triangular facet. There is some new small basin is coming up, and it is kind of blocked. It is kind of little bit blocked by this rock. So now my mind thinks that okay, there is some kind of a lineament is passing through this basin. Maybe I need to go in the field and check whether it's a fault, and then I can mark the orientation of this, and maybe I can see other hills also that whether it is passing or not. And if somewhere near a river, maybe this fault is truncating a quaternary sediment, then I can even date it and put some constraints. Okay, this fault moved that time. So we can put some age constraints on top of this fault. Because if this mass was not here, imagine like that, then this basin would have continued easily. But this is coming into this, and this one is also coming into this. So these two, maybe something is passing. One strand may be passing like this, merging into the one fault plane. Okay. And some of the basins, yes, they are maybe sometimes they are more or less erosional, purely erosional. Now we can see this area also. There are drainages which are coming like this. So if these drainages are just going into the river, it's fine. But if somehow this drainage is falling, making a waterfall and then going into the river, it means there was some kind of a uplift or something which happened. So just by looking at drainages, when we are going in the field, we can get an idea. Okay, this area is stable, or it's some tectonic activity has happened. Because if some drainage is coming, it will make its path up to the river. But if it's just falling like a waterfall, and lot of waterfalls are falling, it means this rock has gone up. That's why it is falling, and slowly, slowly it will make its path, but it will take time depending upon the strength of the rock. So when we are going in Himalayas, we should always be thinking about all these things. And there is another thing. Now there is very interesting thing is happening here. You see that now this basin is totally okay, done. This one has lot of these erosional headward erosion is happening. So you can think of as a landslide or some debris material is coming. Now there is a basin in top of it, which is kind of hanging here. You know, and no doubt that when we are talking about erosions, that is mainly controlled by uh, the strength of the rocks. For example, if we see in Dehradun, right here, there is this big landslide, and there is Stonegad thrust is passing through this area. There is a fault, paleo fault is passing right here. Stonegad thrust like that, and you have a big landslide on top of it, right? Now the idea is if this fault, now you can see this fault is again, you see this drainage basin, this fault is going like this, this fault scarp is going like this. In this drainage basin, the more or less erosion is happening here. But in the adjacent valley, the whole rock mass came down. So these are very interesting questions. Why it is happening like that? What is controlling it? So you see, in this one, There is a big landslide in this one. Only a uh, small portion of this basin is having hardwood erosion. This one whole is going down. This one only here. And there are many anomalies, like that. One more thing I want to show you now. Yeah, there is one more geomorphic feature which is present on top of a mountain. It will look like a hanging this thing, but it is not. So if we go into, yeah, when I first started working, this is basically Renuka Lake. I marked it as a fault. So sometimes, so now you see this is close to Renuka Lake. It is close to Renuka Lake. So if you see this is the top of the mountain, you know, you will think that this is a fault because you have lot of these sag ponds in top of the mountain. You are forming a valley, but I was thinking this is a fault and I will work on it. But later on, I came to know that it's not a fault. You know, so this is again a geomorphic anomaly. You see this, this is a top of a mountain. Something like this is okay, but top of a mountain, you have some kind of valleys formed like this. So my understanding in my mind was maybe some fault is going, and that's why you are forming these kind of valleys, which is forming a linear chain. But that is not true. This is a Sukanjan. This is known as Sukanjan, which is a slowly sinking zone. These are slowly sinking zones. So that signifies that there can be a slow movement of the slope, and someday these you might have some kind of a landslide here. So these are the geomorphic signatures of slow creeping slopes. It may not be a fault. You see this, okay. You can see that this is a forming a linear chain, like this. But these are not fault. These are not due to fault. So in Himalayas, we have we have lot of these river terraces, and then you have these alluvial fans. These alluvial fans are formed along the river. You know, and those alluvial fans can be of both, fluvio-glacial material. It can be a fluvio-glacial material because glaciers have also contributed, and then you have fluvial influence also. Any questions? Yes, mythology also plays a role. As I showed in the first example, in case of Manikaran, that is a good example. I will say mythology plays a role, but joints, how you have these joints are oriented, that also plays very good role. Because if you see that leaf kind of a structure which is formed in Manikaran, it is definitely controlled by the joint orientation. So you need to little bit train your eye, I will say, to distinguish these factors. So now, uh, if you just see right here, you see a lot of vegetation is here. You know, just by looking at the texture, we can say that this is Shivaliks and this is not Shivalik because you have more trees, more greenery on top of Shivalik rocks. But behind that, you can see that, no, it's not. Those are Precambrian rocks, and there is a fault. MBT is passing through this area. Slowly and slowly, as you get experience, you try to understand. Oh, okay, just by looking, and then you can also go in the field and check. Now here also this fault is again, I will say, deflecting. Now you can see that you know this drainage basin is not able to go into back because this rock is different than this. So it is a kind of a barrier here. Otherwise, this basin has must have been this, and its boundary will be like here. Catchment will be here. So because this rock is hard and the fault is passing, so because of that, it is not able to grow into that the back of the catchment. Because lithology is totally different. One is Shivalik, another is Precambrian rocks. Maybe limestone and like that rolls. So yes, both these factors play a definitely strong role in controlling. And then there is tectonics is also going on, active tectonic in this area. So you can see the fault is passing through Nahan, you know, and we have geology department of Nahan on top of fault. You can see right here, right? And now if we see these basins, we see that there is some these linear chains are going, right? Lot of these. This is not fault. Don't confuse it fault with fault. Everything which is linear is a no. It can be bedding. You can have dipping beds. And because of lithology contrast, those are showing as a linear, trace. But it's not a fault. But on the other hand, if it is a fault which is passing through this bedding, then it's a problem for us because we are assuming it's just bedding. Then we need to look for some geomorphic markers. Because in the books it's very easy to define a fault or a fold, but in the when we go, then it's tough to find a fault, especially in Himalayas. I mean, now one more thing, see this drainage now. This drainage basin came, and here it has not gone. See, this river is coming here, but the drainage basin might have shifted because of tectonics. Otherwise, this would have continued like this. Here it is very, very a narrow V-shaped valley of the river. But as it crosses, it flows. You can see as it crosses this zone, as it crosses this zone, it becomes, it starts meandering. So these are all these things, I think, can be worked out and can be seen that how these bases are working, how the lithology is playing control, how the tectonics is working in this area. And on top of that, you have a driving force. The driving force here is water, right? Tectonic is trying to build up these mountains. Water is trying to cut it down. And whenever there is active fault or tectonics, that is deflection, some kind of a deflection. And then we try to understand through geomorphic markers where is the fault, what is the anomaly, things like that. So in Himalaya, yes, there are lot of work which can be done. There are lot of anomalies which are present. You know, and you guys are lucky because you are just in the foothill of Himalayas. You don't have to travel much. Okay. So now the idea, we have understand that a drainage basin can be very older. It can have effects of lithology. It can have effects from, it might have seen lot of cycles as we discussed in the morning. Now we need some kind of a numbers. How this water is flowing this through this drainage basin, and some numbers which can tell this is normal, this is tectonic, and this is something in between. You know, so the water is flowing. We need some kind of a mathematical numbers. Now, for that, what we can do is all of us know that what is vector and raster data. So in raster data, we can have digital elevation model. Digital elevation model, you have X, Y, and Z, right? And in X, Y, Z, we have softwares like ArcGIS, QGIS. In that, you can make a drainage system, to the dam. And we can develop some, or we can use some tools to identify if these numbers make sense or not. So that is what we are going to do. So if you have a computer, you can install QGIS. It's freely available, and you can calculate these. So now what we are doing is, now the exercise is what we are going to do. Basically quantifying drainage network structure. So the objective is stream order provides an objective method for describing the topological structures of a drainage basin. It reflects how streams are arranged from small waterhead channels to the main trunk, thereby defining the network's hierarchy. This quantitative approach allows researchers to compare drainage basins across different regions and geological settings systematically. Till now, what we were doing, I was just showing you, right? That this is looks anomalous. Now we are trying to put some numbers. So foundation for analysis, stream order is critical for calculating fundamental morphometric parameters. So we are going to do bifurcation ratio, stream length ratio, drainage density, stream frequency. Without stream order, basin morphometry cannot be quantitatively assessed. Geological and structural controls, structural disturbances, faults, joints, fractures, influence stream pattern and branching. Right? These are you can say structural fault. If it is an active fault, it can come into tectonics also. So joints, you know what is a joint, right? So joints are basically parallel sets of these, planes. You know, generally in Himalayan rocks, for example, in lower Shivaliks, we find 2 to 3 or sometimes 4 to 5 sets of joints. Right? There is a difference between bedding plane and a joint. It is very important in the field when you take dip and strike data that first of all you should first find what is the bedding plane. Where is the bedding plane? Sometimes we can confuse a joint as a bedding plane. So you need to take care of that. So tectonic uplift, active uplift creates distinctive drainage patterns and irregular branching. If there is some kind of a upliftment, so that will create a different type of a drainage pattern. Lithological variations, different rock types control stream development and network complexity. So the best example, as I just showed you, lithological variation was Manikaran. In Manikaran you saw that leaf kind of a drainage pattern. So that is definitely lithologically controlled, right? If that leaf is broken in between, then I will say there is a fault. So that is a good example which you can see that, you have lithological. And then drainage rearrangement, stream piracy, network reorganization reflect geological evolution. High stream order accompanied by irregular branching pattern often indicates structurally controlled drainage networks common in tectonically active regions like in the Himalayas. Hydrological characteristics by stream order. Higher order streams drain large areas, carries greater discharge, have gentler slopes, exhibit higher stability, lower erosive power compared to headwater streams. Lower order streams more numerous throughout the basin, steeper and more erosive, dominant contribution to sediment supply, sensitive to land use changes, and responsive to rainfall variation. So stream order can help to interpret the hydrological responsiveness and sediment dynamic of a basin, providing insights into how water and sediment move through the landscape. Watershed management applications, flood risk assessment, stream order helps identify critical flow pathways and areas vulnerable to flooding during extreme events. Erosional susceptibility, lower order streams control slope erosion while larger order channel transport sediment downstream. Ecolo- Ecosystem management, different stream orders support distinct ecological communities and require tailored conservation strategies. Channel stability analysis, understanding stream order help predict channel behavior and plan infrastructure accordingly. Now, these are some of the practical steps generating stream order from the digital elevation model. So, what is a dam? All of us know that dam is a digital elevation model, is a raster data set. So, in GIS, we have two types of data set, whether it's a vector data or a raster data. So, dam is a raster data where each cell contains elevation values representing the terrain surface. It serves as the foundation for all hydrologic flow modeling. Quality measure requirements free of artificial sinks. Sometimes these dams have errors, they have sinks, and pits that interrupt natural flow. These are some small errors, these are small errors in the data which we need to remove before doing any processing. Okay. Appropriate resolution for your study scale, accurate vertical and horizontal datums. Essential pre-processing. Before flow analysis can begin, the dam must be conditioned to ensure continuous flow paths across the entire surface. Critical first step, all sinks to eliminate depressions that would artificially trap water and prevent realistic downstream flow modeling. Okay. So basically what we are doing in this, there are uh, in raster model basically uh, there are kernels. Kernels can be used for calculating slope, aspect, things like that. So when you have a raster data, so let's say we have a some elevation, digital elevation model, DEM of any area. So basically these are the columns and then you have rows. So these are the different cells which are present in a raster. So we can have an algorithm which is known as kernel, in which we can take nine values, these nine values of elevation, and then we can calculate a formula to know the slope of where is the slope of these elevations, you know, and then we can also have we also want to know, if the elevation is higher because all these cells have X, Y, and Z value. Z is your elevation. So when we have a raster file that has a lot of data points, so what will the computer do? It will take a matrix 3 by 3 and it will try to calculate at every cell what is the slope direction and in which direction then water will flow, right? So that is the basic calculation it will do. And slowly it will calculate in each cell what is the direction of the flow. And then it will know in which direction the water will flow. And before doing this, if there are some errors, like we have, some kind of a error, then what will happen if let's say this value is some kind of a sink, error sink, it's a sink. So all the water will just go inside this. Nothing will come out. So, so we need to remove these errors, by doing pre-processing. What we can do, we can put some dummy values, or we can say that no value is null value, so that this is not a sink. If it is a sink, then all water will just go here. Nothing will come in this side. So that is just to remove the errors from the dam. So that is the first critical step. Fill sinks to eliminate depressions that would artificially trap water and prevent realistic downstream flow modeling. So first step will be fill the dam to remove sinks. Identify the problem. Raw dams often contain artificial depressions or sinks, low points that trap water flow due to data errors or processing artifacts. Then apply fill tool. Use RGS tool spatial analysis to automatically raise the elevation of sinks cells to their pour point, ensuring water can flow out. Validate output. The filled dam eliminates artificial stops in water flow paths, creating a hydrologically correct surface ready for downstream analysis. So this tool location is in spatial analysis tool, hydrogeology and fill in RGS. You can go there and you can remove all the sinks. Now calculate the water flow. The D8 method, the flow direction tool implements the D8 algorithm, which evaluates the 8 neighboring cells surrounding each grid cell. Each cell is assigned a directional code indicating which of its 8 neighboring receives flow based on the steepest descent path. So we have, basically raster file is just a file which has a lot of numbers. So this software is just trying to understand in which direction the water will flow. So understanding the output, the resulting flow direction raster uses power 2 of coding. One is east, two is southeast, like that. These are different directions. This raster becomes the routing network for all subsequent hydrologic analysis. So the tool location is spatial analysis tool, hydrology, flow direction. And then this coding is done. We run this algorithm on top of this raster layer and we can get the fractional coding. Now calculate flow accumulation. Input data, flow direction raster defines the routing network. Accumulation process, a tool counts all slope cells flowing into each cells. Stream identification, high value reveals natural drainage channels. The flow combination tool creates a raster where each cell value represents the cumulative number of upstream cells contribute, contributing flow. Cells with high accumulation values indicate potential stream channels and drainage pathways. So the tool location is spatial analysis tool, hydrology, flow accumulation. And now we can see that, in each cell, it has calculated, the software has calculated the flow direction, and it is showing in this first diagram the flow direction. And then you have flow accumulation where the flow will come, from different cells. Now we can see that there is a value of 7, 5, and 20, 24, 25. So the water is coming and it is going into that cell. And then next step is define stream network, applying the threshold concept. Not every cell will accumulate flow in stream. Threshold values separate actual stream channels from overland flow paths. So one is choose threshold value, select accumulation value based on dam resolution and landscape characteristics, commonly which ranges from 50 to 500 cells for a resolution of 30 meters. Refine and validate. Compare derived stream with aerial imagery or reference data. Adjust threshold if network is too dense or sparse for study objectives. So threshold selection is iterative. Lower values create denser networks. Higher values show only major channels. So now, basically, after doing this step, you are able to generate the stream order. One, two, like that, three and four. Okay. Now assign stream order. That is the fifth step. Using stream order tool, the stream order tool requires two input, your binary stream network raster and the flow direction raster that defines the connectivity between stream segments. Choosing your method, Stoller method. We have discussed the Stoller method before also. So first is your headward stream, no tributary flowing in, and two plus higher order formed by confluence of equal order streams. So a output a raster where each stream cell contains its calculated order value, revealing the hierarchical structure of your watershed. You can see that. So if we are one is mixing with one, then you have second order, and then two and two is making the three, three and three like four. Okay. So now in the final step, we convert to vector format. Start with the stream order raster. Your classified stream network currently exists as gridded raster cells with order values. Convert to polylines. Use streams to feature tool to transform raster streams into vector polyline features suitable for mapping and spatial analysis. Optional smoothing applies smooth line tool to reduce stair step appearance and create more natural looking stream lines for professional orthographic output. Because we are working in this raster, in raster you can have these cells coming look like a stream. That is sometimes it is not true. So that is why we need to do some kind of a smoothing so that it looks natural. So vector format enables attribute queries, network analysis, symbolizing by order, and integrating with other geographic datasets. So first is this bifurcation ratio. The bifurcation ratio expresses the relationship between the number of streams of one order and the number of streams of next higher order. The bifurcation ratio BB is the fundamental morphometric parameter used to quantify the degree of branching in a drainage network. Proposed by Houghton in 1945 and widely applied using Staller's ordering system. A bifurcation ratio provides insights into the structural, lithological, and geomorphic characteristics of a watershed. Because drainage network reflects the influence of geology, climate, and topography. Bifurcation ratio serves as an important indicator of tectonic control, drainage evolution, and landscape dissection. So the formula is RB is equal to NU upon NU plus 1. Here NU is the number of streams of order U, and NU plus 1 is the number of streams of the next higher order. This calculation is based on Staller's stream ordering system, the most commonly used method in geomorphology. Now here you are given the some handouts on which you are to calculate this thing, bifurcation ratio. So generalized classification of bifurcation ratio. So if the bifurcation ratio is less than 3, it is classified as low. Between 3 to 5, moderate, and more than 5, it is high. So low indicates homogeneous rock with structural control, youthful drainage, and a dendritic pattern. Moderate normal drainage behavior, Moderate structural influence common for most basins, and high value represents strong structural and tectonic control. Elongated basins, valleys, rectangular patterns, active tectonics. If you, let's say your number is RB, this bifurcation number is more than 5, let's say you have 10 or more than that, then yes, you can think of that, yes, this drainage basin is affected by active tectonics. So now we are getting some kind of a number. Previously, we were just having a visual look of different basins. Now, this bifurcation ratio is helping us to identify basins which are can be active. Okay, so this is your first exercise. You need to mark the stream order and calculate the bifurcation ratio. So I think we can also start the practical now. Okay, so all of the students must have been given the practical sheet. So now you can start doing the practical. So count the number of streams in each order for calculating the bifurcation ratio. So you need to count the number of streams in each order. So you can use this formula RB is equal to NU upon NU plus 1. First order. Okay, more numbers. Okay, I will write actually. Okay, wait. Okay. First order, first order, second order, third order, fourth order. So what is the value for this one? First order. Okay, 68. So the value is 68. What is the value for second? So everybody got these numbers? Same? Ishmeet, did you got the same numbers? What is the value you got? 70? Okay. Rest of the numbers are same. Chalu? Huh? क्यों? Okay. Okay. You can again try to see carefully. So I will wait for 2 more minutes, I think, and then we will show you the result. Let's see. Okay. So now 64 for first orders, second order 17, third order 3, and fourth order 1. Okay. So the ratio calculation between first and second order 3.76, 3 to second to third order 5.67, and between 3 and fourth it is 3. So mean bifurcation ratio uh, you can calculate is around 4.14. Okay. So now based on our classification, what type of basin is this? Moderate? Okay. So if the bifurcation ratio is between 3 to 5, this is a normal drainage behavior, moderate structural influence, common range for most basins. Okay. So interpreting the bifurcation ratio results. So high structural control, a mean bifurcation ratio value of 4.1 is considered high, implying strong structural control on drainage pattern. Fault guided drainage lines are guided by faults, joints, fractures, and lithological boundaries. Tectonic activity, the basin is likely located in a tectonically active or structurally complex terrain. Restricted branching, stream branching is restricted by rock resistance or structural alignment. This pattern is typical of Himalayan basins, especially in areas with high relief and active incision where geological structures dominate drainage development. So next is this is the second exercise, hypsometric integral, that is basically measuring landscape evolution. So what is a hypsometric integral? The hypsometric integral, which is HI, is a dimensionless geomorphic index that expresses the distribution of elevation within a drainage basin. It quantifies how much of the basin's original relief remains after erosion. In simple terms, HI tells how high or low a basin stands relative to its total relief, where E mean is equal to mean elevation, E max is the highest elevation, E minimum is the lowest elevation. So HI value ranges from more than 0.6, that means that is a youthful stage, 0.35 to 0.6 it's mature, and less than 0.35 is old. So in youthful, high relief, steep slopes, and tonically active, if the value is more than 0.6. And if it is mature, then moderately dissected, transitional, low relief, strongly eroded, and stable. So you can write the formula for hypsometric integral. Now you need to calculate the hypsometric integral. So extract elevation values, derive minimum, maximum, and mean elevation from them or topographic data. Apply the formula, use hypsometric integral equation with extracted values. So now you can do the calculation, right? You can do the calculation in the given sheet, and the formula you need to use is this one. This is your hypsometric integral HI. So now you are given this topographic sheet in which you can calculate the different parameters. It's basically it means mean elevation, and Emax is the you need to find the highest elevation contour, and then E minimum is the lowest elevation. So you can find these numbers in the given maps. कर लिया आपने? Just wait for others to do. So what is the value you got for HI? 0 point? Any other number? Any other value? So calculating the hypsometric integral. So extract elevation values, derive minimum, maximum, mean elevation from the dam or topographic data. Apply the formula, use the hypsometric integral equation with extracted values. So E mean is 1300 meters, minimum is 800 meters, E max is 1800 meters. So the HI comes around to be 0.5. An HI value of 0.5 indicates a mature stage of a geomorphic development. E minimum, okay, so, okay. So we can see that HI value is around 0.5. That means it's a mature, moderately dissected and transitional. Mean निकालना है. We will help you. Elevation. So a hypsometric integral value of 0.5 indicates that the basin is in a mature stage of geomorphic development, lying midway between youthful and the old landscape. The terrain has undergone substantial erosion, yet a considerable portion of the higher elevation still remains. It's not showing, the screen is not showing. कर देते हैं. So, hypsometric integral value of 0.5 indicates that the basin is in a mature stage of geomorphic development, lying midway between youthful and the old landscape. The terrain has undergone substantial erosion, yet a considerable portion of the higher elevation still remains. So, geomorphic balance, valley incision, and slope retreat have reshaped the topography, but the basin has not degraded into a low relief surface. Both elevated uplands and moderately expanded valley floor coexist. Tectonic equilibrium, moderately tectonic activity with neither dormancy nor high uplift. Uplift and erosion operates in dynamic equilibrium, maintaining relief while steadily reducing it. In hydrological response, moderately hydrological responsiveness with discharge patterns neither excessively flashy or nor overly subdued. Sediment transport and runoff generation occurs at intermediate levels. This pattern is characteristic of many mid-latitude altitude Himalayan watersheds where structural influence is present but not dormant. So these are the different interpretations in terms of geomorphic balance, tectonic equilibrium, or a hydrological response. Now the next uh, morphometric parameter is valley floor width to height ratio VF. So measuring valley incision, the valley floor width to height ratio VF is an important geomorphic index used to evaluate the degree of valley incision and the relative dominance of tectonic uplift versus erosion. It quantifies how narrow or wide a valley floor is compared to the height of its bounding valley walls. So the formula is VF is equal to 2 VFW divided by VEIT minus EV plus VERT minus EV, where VFW is valley floor width, VLD is left divide elevation, VRD is right divide elevation, and VE is the valley floor elevation. A deeply incised V-shaped valley produces a low V value, whereas a U-shaped valley yields a high VF value. So now, can anybody will tell me in a tectonically driven area what kind of uh, valley shape we are expecting? Whether we are expecting a V shape or a U shape, right? We will expect a V-shaped valley in a tectonically driven area. Okay. So this parameter will help us to understand this thing. So interpreting VF values, low VF, that means less than 1, represents deeply incised valleys, narrow V-shaped valleys with steep side slopes and strong vertical incision. Typically in tectonically active regions, areas experiencing rapid uplift and young fluvial systems, common in mountainous terrains like the Himalayas, right? So deeply incised valleys, the VF value will be less than 1. And where we have the moderate, that is the transitional valley. So in moderate, the VF value will vary from 1 to 2. Partially widened valleys that are neither sharply incised nor fully mature indicate balanced uplift and erosion with a moderately active geomorphic conditions. Represents evolution from youthful to a mature stage. High VF values, if the VF value is more than 2, wide U-shaped valleys, broad valleys floors with gentle side slopes, characteristic of old or tectonically inactive landscapes, and low region relief regions. Erosional dominates over uplift, producing stable widened valleys. So if we have U-shaped valleys, the erosion has taken over in that valley, and that has produced a stable and widened valleys. So significance of VF in tectonic studies, indicator of tectonic uplift. So this is also important in areas where we have a recent tectonic activity, because if the area is uplifted, then we will have a lower VF values, signaling strong uplift and rapid erosion, making VF one of the most widely used morphotectonic indices for identifying active tectonic zones. So this is very important. Valley evolution studies, by comparing VF values across a basin or between different basins, researchers can determine various stages of valley development and landscape maturity. Complements other indices when used with the mountain front sinuosity, HI hypsometric integral, and stream length gradient index. VF contributes to a holistic landscape understanding. In hazard assessment, low VF values often have steep slopes, prone to landslides, flash floods, and strong channel instability, critical for risk management. Okay, so now you are given these problems and these calculate the VF for these valleys. So if you have a digital elevation model, using a software, if you think there is you want to calculate, so you need to have a slice. You can take a slice of elevation, and you can extract the elevation values from a digital elevation model where you want to check this valley floor width ratio VF, and then you can produce these kind of elevation graphs, and from these elevation graphs you can uh, figure out the basic parameters which are required to calculate this VF. So now you are given the problem set, and you can calculate the VF for these uh, five profiles, and then we will discuss. And you are also supposed to write which valley you think is tonically active and which one is not. Okay, so now you can do the calculation. You can write the interpretation. What are these values now? उसका इंटरप्रिटेशन भी कर दो ना, कि 1 से लेके 5 तक जो वैल्यूज हैं वो कैसे हैं. So once you do the calculation, you can use this table. You can use this table. If VF value is less than 1, that means it is deeply incised valley. If the value is between 1 and 2, it's mature. If it is 2, then more than 2, then it is a widely U-shaped valley. So you can this use this interpretation table to classify your valleys. So what are the values for, okay, 1, 2, 3, 4, 5. So first one, 0.2, third, 4.39, 4.15, 1.5, 1.5. Everybody got the same numbers. Okay. So now you can classify also. This valley deeply incised means tectonically, you can say tectonically active, huh? Deeply incised. This one transitional. This one U-shaped, है ना? So no tectonic activity like that. This one, अच्छा second वाली भी 2 से ऊपर है. Okay, U-shaped है. This one transitional, deeply incised है. Deeply incised, that means tectonically active. है ना? So now you can see that by calculating these numbers, you are getting some kind of a sense that how this area is big, whether it is tectonically active or whether it is not. So we are getting this kind of numbers, and that is helping us to understand the landscape of an area, whether how it is deforming, whether it is in which or whether it is in uh, active actively deforming. So these were the numbers which were given to you, and these are the answers: 0.2, 2.3, 4.3, 1.5, 0.15. So these are the interpretations. Okay. So valley 1, yes, V-shaped. Valley 2 is again a little bit moderate. Third is totally U-shaped, Third is totally U-shaped. Second is a little bit U-shaped, yes. Fourth and fifth again transitional morphology. Fifth is again deeply incised V-shaped valley. So even though this looks very, this profile looks very normal, but let me put a question here. Let's say I want to build a dam in these, let's say this is a location of a dam. In which valley I need to build a dam? Which is the safest valley out of these five where we can build a dam? Which one? This is safe, and number two, this is also safe. Huh? What if I'm building a dam here because it's a V shape? So that gives us an idea that maybe this is tectonically active, or something can happen. Or maybe if the fault is there parallel to the dam, then this you can have a activity and the dam can be broken. So even though this parameter looks very normal to us, we just do calculation, but when we apply these things in life, in practical, then we get more insight into that area, you know. So what is the difference between 3 and 4? What is the difference between 3 and 4? In 3, we are getting a value of 4.3, and in 4, 1.5. So 3 is totally safe. 3 is more or less safe, right? Because it's a huge shape. It has wide width also. Yes. What about 4? So yeah, this is a transitional and neither deeply incised nor very wide. indicates balanced erosion and uplift, often seen in moderately active tectonic settings. It is again, it can be seen in a moderately active tectonic setting. These values mature with moderate incision or a moderate tectonic influence. But uh, when we are considering big structures like dam, you need to see a larger area. If, even though maybe the fault is not passing through this valley, but let's say within 1 or 2 kilometer area, there is a big fault. And if you see some geomorphic markers that it is active fault, then you need to do more studies in order to understand what is the reoccurrence interval of that fault. That means if a fault is having earthquake after, let's say, every 200 years, or is it having earthquake after every 100 years, or it is like, let's say, every 50 years. So we need to understand whether this fault is active. Okay, if it is active, whether it has one earthquake in 1,000 years, then we can build a dam. Because one earthquake came in 1,000 years back, next one will come in 1,000 years. So till that, my dam is safe for, let's say, 100 or 200 years. But if the earthquake is coming within 50 years, and I'm making a dam for 100 years, then it can be a problem, right? Or then I may need to take some uh, structural design. I need to design my dam in such a way that it can take the shaking, because you will have uh, shaking of the ground, and the water will also, that the water behind the dam, which is also shaking during the earthquake, that will create a big impact while the earthquake is happening. So those parameters need to go into the dam design. That what kind of shaking we can expect in this area when we are building a dam. So all these are very, very crucial geological feasibilities which are done when we are constructing a dam. Okay. So, and one more point here I want to say, that in the area of Punjardun, we have done these morphometric analysis, and we have seen some areas where we are finding V-shaped valleys. That means that area is rapidly uplifting, and the role of active tectonic is there, you know. So it also helps to identify, and we have also find out some faults are active in this area also. So in Pinjordun, there are a lot of these active faults are there, you know. So these things are important. Like we also did this flow analysis. If you want to buy a house, let's say around Chandigarh, you want to buy a house. Maybe you had a deal. You want to check whether when the rain happens, does my house will have flood. The water is coming from all the directions. So you want to have you can do this kind of analysis simply by having a digital elevation model, and you can see whether my house is in a low-lying area. If the flood comes, the water will come. So these kind of analysis are very, very important. One thing is that the flow, the flooding will not happen. Second is how far it is from a fault or a zone, and then you can also make your house a earthquake resistant house, because we are living in a very seismically active zone. The Himalaya in Himalaya is a seismically active zone, so we need to build our house in such a way that it is earthquake resistant. For example, in Japan, you have a lot of earthquakes coming, but in Japan they have designed their buildings so that they can take the shaking, right? So these are the things which we can keep in our mind. So next is the morphometric parameter is mountain front sinuosity. So mountain front sinuosity is a geomorphic index used to evaluate the degree of tectonic activity along a mountain pediment or a mountain alluvial plain boundary. It measures how straight or irregular the mountain front is. So this is the mountain front sinuosity, where LMF is equal to actual length of the mountain front irregular, and LS represents straight line length. And the tectonic interpretation is if the value of SMF is between 1 to 1 point, then it's a high tectonic 1.6 moderate tectonic activity, um, low activity. In tectonic active regions, wall scarps and active uplift keep mountain fronts straight and sharp. In inactive regions, erosions create irregular sinuous shapes. Okay. So now in this is the conceptual model basically. So if the mountain is active, then active fault driven uplift mountains maintain straight sharp mountain fronts by continuously rejuvenating the topographic boundary between the mountain terrain and the adjacent basins. Okay. Erosional dominance activity increases. Fluvial and mass wasting processes dissect the front, creating irregular sinus boundaries that reflect long-term denudation. So mountain front geometry serves as a diagnostic proxy for competing forces shaping active orogenic margins. So you can do this calculation. Classification and geomorphic significance. So if the value is between 1 to 1.5 highly active, between 1.5 to 2.5 moderately active, and if it is more than 2.5 it is low activity. Okay, you so now you can do the calculation. You are given the problem set. Okay, you take some time to do the calculation, then we will discuss this. So, so what is the value? 1 to 5. So what is the value for one first? 1.07, 1.22. ठीक है, सबका यही आंसर है. So first one is 1.07 है ना. Extreme basically yeah, everybody understood what does it mean actually, right? किसी को डाउट तो नहीं है इसमें माउंटेन फ्रंट सिनोसिटी है ना. So basically what is happening if there is a mountain front, right? If it is going up like this. So the front will be very straight if it is new tectonic activity, right? And if it is older tectonic activity, then lot of sediments will cause the sinus front. The mountain front will be more sinuous. So, like for example, we are looking here, right? If there is a fault, which displaces this boundary like this, so this front will look very straight. If the mountain front is looking very straight, that means, you know, it has just gone up. But if this tectonic activity is very older, then what will happen? Lot of sediments will come and it will cover the mountain front and it will be more of a zigzag pattern. So just by looking geomorphologically or just by having a look at the mountain front, you can understand that whether it's very active or not, you know. And then this you can use this parameter to understand the activity of the mountain front. Okay. So I think this is the map of Kordwar area, right? Kordwar. So this example is taken from the Kordwar area. So extremely straight segment one, which is this one. Segment one is showing extremely straight segment, very strong tectonic uplift, minimal erosional modification. Segment two, highly linear active fault control. This one is again showing. Segment three, slightly more sinuous but still very low. Strong structural control. Segment 4, 1.24, mostly sinuous among all but still in active range. And segment 5, 1.16, highly active steep segment, sharp at chronic front, preserving straightness. Okay. So this is again a kind of a parameter. By looking at it, we can try to understand how any area, the front is behaving in any area. So morphometric analysis key takeaways: stream order provides hierarchical classification of drainage networks, essential for understanding basin organization and hydrological behavior. Bifurcation ratio reveals structural control and tectonic influence on drainage patterns through stream branching analysis. Hypsometric integral identifies erosional stages and landscape maturity by measuring elevation distribution within basins. And valley floor indicates tectonic activity through valley incision measurements and morphology assessment. And mountain fronts anisotropy evaluates tectonic activity along mountain fronts by measuring boundary straightness versus irregularity. These morphometric indices work together to provide a comprehensive insight into landscape evolution, tectonic activity, and watershed management priorities. Their combined application enables systematic analysis of drainage basins and geomorphic processes. So if you have any questions, you can ask. So basically, we can use morphometric analysis, and then there is one more thing, which is like we can use remote sensing data. For example, cartograph data. Now we will do an exercise in which we will show you some of the anaglyphs. Basically, in that you can see an area, you know, in 3D. Like maybe you have seen a movie in which a 3D movie देखा है कभी किसी ने? So similarly, in this, you will once you set your eye, you will be able to see in a 3D vision any area. And then why we want to do this? Because it gives you a bird eye view of any area. Then you mark different river terraces. You can mark different alluvial fans. Then you click in that area. You can mark the fault. We'll do a small exercise in which you will just see the anaglyphs, and we will put the PPT, and then we will provide returns. So, and in some areas, If you want to find a active fault, nowadays people also use drones. Drone survey can be done. So with the help of drone survey, you know that you can generate contours, very high dense contours. Contour interval of let's say 2 centimeter or 3 centimeter can be generated using a drone. But on the other hand, like the Google Earth or other topographical series, the contour interval is on the height of 20 meters. So that's why the use of drones in geology nowadays increasing, because you need to do a lot of surveying. If you need high precision cloud point, then you need to use the drones. And drones are also used to mark active faults. You know, you can mark a active fault because for an area, if you have a high resolution depth, then you can clearly see from where the fault is passing. It helps you a lot. But in order to fly a drone, you need a license and you need to do a lot of paperwork, and then only you should fly a drone. And there are some areas where you cannot fly drone, so you need to check those areas, where we can fly drone. Okay. So now what we will do is we will show you some remote sensing data in which you can see 3D. Okay. If you have any question, you can ask. Otherwise, we can go for the other practical. Yes. No, no. So yeah, what we have done is, yeah, you can measure the length from here, right? But when you are doing this exercise in the software, like yes, in the software you can measure the length by applying this. So if you follow this, then you can calculate the length in a software. Yeah, you can digitize. Yeah, you can digitize and you can calculate the length, because these exercises can be done easily in computer, but we have made it print out for you so that you don't need a computer. But otherwise, all these morphic metric indices, you need like software, RGS, MATLAB. So you can do these exercises on a computer. Okay. Okay. So now we will show all the students can wear the glasses, and you can have the depth perception, stereographic view of the. Yeah, we can put the computer here, and students can come one by one, and or maybe in a group of two. We can put here also. So okay. So you can come wearing the 3D glasses. If you have glasses like this, then you need the overhead glasses, and then you can have a look at the this anaglyph. Ashok, Aju, you can come. Yeah. इसमें देखो जरा लगा के आप what you are able to see 3D perception. And if you see here, maybe you were able to see some. Now maybe you can see this. Now, sir, if you focus in this figure, then you will be able to see a performance curve, basically. And you can also see close to the river, various river terraces are present. You can see along this Giri river. there are river terraces. You can see the elevation of these river terraces is varying. So what you can do is on computer basically you can mark the different geomorphic features. Okay. So uh, these photographs basically helps you to make geomorphic maps of the area. If you want to make large scale geomorphic maps or you want to uh, mark the faults or lineaments on the topography, then these maps helps you a lot because not everywhere you can go. Um, but so we have made these geomorphic maps of this area using this remote sensing data. हम्म, ठीक है. हाँ, इसको यहाँ पे बताओ थोड़ा सा, यहाँ पे जैसे रिवर टेरेसिस देख सकते हैं ना, ऊपर नीचे, ये शायद डेप्थ परसेप्शन दे दे. देखना क्या है, देखो इसमें तुम्हें यहाँ पे देखना है कि अगर आपका जो है यू आर एबल टू सी इन 3D, नो, you are able to see something in 3D, like you can see here the river terraces. So are you able to see the depth perception? किसी भी एरिया में जूम करके देख सकते हो आप. You are able to see this fault. डेप्थ परसेप्शन आ रहा है आपको? ये देखना है आप. देखो इसको. नहीं नहीं, यहाँ देखो, रिवर के पास देखो. देन you should try to see close to the river and whether you are able to see the some elevation or steps. थोड़ा आगे पीछे हो जाओ, ऐसे ऐसे कर सकते हो, अपने अपने आप को करना है, कंप्यूटर को नहीं. यहाँ पे देखो तुम्हें डेप्थ परसेप्शन आ जाएगा. इस ऊपर दिख रहे हैं ये घर, ऊपर को उठे हुए हैं. Then once your eye is set, then you can see the whole area into 3D. बट जब तक आपका आई परसेप्शन नहीं आता ना, तब तक वो 2D प्ले फिगर ही दिखेगा. बट वंस योर आई इज सेट, देन यू कैन सी द डिफरेंस इन हाइट. एलिवेशन का जो डिफरेंस है वो दिखना शुरू हो जाएगा आपको. दिखा? कुछ नहीं दिखा, कोई बात नहीं. नहीं, मुझे तो दिख ही जाएगा. हम्म. जैसे यहाँ इस तरफ आप देख सकते हो, ये ऊपर है, ये नीचे है. ये ऊपर है, ये नीचे है. ऑन ही, अच्छा हो गया ऑन, ठीक है. हम्म. नहीं, आपको ये देखना है, जैसे यहाँ पे देखो, ये ये जो अलूवियल फैन है, दिस इज रेज्ड. सो हाँ, यू जस्ट ट्राई. डेप्थ परसेप्शन नहीं आएगा, तब तक आपको कुछ नहीं दिखेगा. 2D ही दिखेगा, 3D नहीं दिखेगा. ठीक है. जैसे अभिषेक, मेरा जो पीएचडी स्टूडेंट है, उसको 1 साल तक दिखा ही नहीं कुछ. उसके बाद उसको समझ में आएगी क्या देखना है. इट टेक्स टाइम. So this cartosat data basically we purchase from National Remote Sensing Center, and we have lot of scenes of Himalaya, and you can there is a software known as NV, in that you can make anaglyph, and then you can have a 3D depth perception of the area. So this helps you to map large areas, and then once you have identified a fault, then you know where to go in the field. you will take a car, or you know where to go, where to do the field work, because then in the field you will see where is the fault. So before we go to the field, we plan our field, where we want to go, where we want to stop, what we can expect to see in the field. Okay. So in this image, I think we can show you. In this image, the Yamuna Tier fault. You know, the Yamuna Tier fault is also visible in this image. You see, are you able to see this line? You see this line here? This line is there, and this small rivulet is shifting. So basically, when I was telling you, right? I was telling you that we have put a trench across a Yamuna Tier fault. So in this image, this is the Saton landslide right here. I was showing you in the morning. This is the Saton landslide. You saw in the morning. So now, if you see this image, you know, if you just little bit focus, you able to see this linear. You see this linear line. You were able to see, and then there is a river which is coming like this. Now it is deflected right here where the fault is there. So what we have done is we trace this fault in this river, and where we want to put the trench. So in the trench, when we put the trench, we can see that one layer is coming like this, and there is a totally different rock across the fault. You know, so this remote now you can see this is a jungle. If you go in the jungle, you will be not be able to figure out what is a fault. Because you will see trees, leaves, because you cannot distinguish that something is linear is passing through this area. But with the help of remote sensing data, high resolution data, you can see the lineament. And actually, this is an active fault. We have dated this fault, but we have not published it, and we will publish it soon. Okay. So this is the first trench on the Yamuna Tier fault. Before that, people were talking about that, yes, there is a Yamuna Tier fault, but they have not marked, or they have not put a trench on the fault. So we have put the trench on the fault using this data. you know so in our in geology, basically, if you have a trench on a fault, because then you can get more information, from the fault. So you can see clearly a live example where this fault, this remote sensing data, and secondly, you can see other faults, you know these faults which are intersecting the small landslide. And then you can also see the this bigger scarp. You see this scarp. We saw that in Google. So if you see carefully, this is the scarp of this Satongad fault. This is following like this, and there is a Sirmaur College on top of this backhill facing scarp. So now you see this, right? You are able to see now the scarp is very clearly visible. So this is again is a example of tectonic scarp. Now the question is, so many people are living in Dehradun, close to Missouri, and we have so many faults which are present in the very vicinity of a huge population. So these are very important questions, for geoscientists to understand. So all these alluvial fans, you can see these different alluvial fans. These are very old alluvial fans. So all this material is eroded and deposited in this Pinjor Dune, and people, stay in these areas. So there are, you can see this fault is coming in this valley. So a lot of these geomorphical features, or lot of these topographical features which we see, they have evolved through time, right? They have evolved through time, and we need to understand what's what's going on in the area. Okay. So now you can spend some time looking at these pictures, and it takes some time to see the 3D perception. Once you have it, then you will not lose it. I mean, you will understand, okay, I can see the 3D in this. Okay. Okay. Thank you.